All right, so you guys, starting systems. Like we joked around, all you need to know about the starting system is it starts the car. And if it doesn't start, then replace the starter. Now, of course, there's a lot more to it than that. So just to give you a step back in time, it's kind of fun just to talk about it. Before we had the electric starter motor, we used to actually have to put the crank in there. So it'd be like almost be like a speed handle wrench, if you've ever seen one of those, where you can do this. So you,
Chitty bang bang.
Chitty chitty bang bang, huh?
That's what he racks his knuckles on. He's trying to start the lady's car.
That makes sense. I didn't actually know about that. That should have to be a mandatory part of the curriculum. Now, just so you can understand for reference, perfect. I'll take it from there.
Required for automotive now.
So you'd get in the car, you'd turn the key on, because that was turning on the ignition, right? That meant like you'd enable the spark. Before you turn the ignition on, the spark was not enabled. Thanks, Ron. Then you'd go out there with your crank, because now that your ignition is enabled, it still has no way to compress, right? We got to compress the air and fuel in the cylinder. Assuming it has fuel, right? So that's another requirement, right? And then when it gets up to the top dead center of compression, we need to spark it. Make sense? As soon as we spark it with the compressed air and fuel, then there should be rapid expansion and combustion, which will push the piston down, and now the engine will run on its own power. But even if you turn the key on and enable the spark, and let's say it's old, it's carbureted, the fuel's always enabled on a carburetor. There's no old school, there's no fuel shut off. It's just you kill the ignition, right? So that's why they say, get in and turn the ignition on, because that's literally all you used to do. Then you'd still have to have a way to turn the engine to build the compression for the first few moments. And then once that compression did its thing and the spark did its thing, then you no longer need the starter, right? So going way back in the day, you'd turn the ignition on, and then you'd put the crank handle in there, and but you'd be fighting the compression. So when you're pushing on the compression, it's really hard to do. And then once it catches and the compression comes up and the spark ignites the fuel, then all of a sudden, boom, it would try to like kind of kick you back. Just like kickstarting a bike, yeah. And once in a while, if you ever kickstart a motorcycle, once in a while you get it where it'll kind of start but not quite start, and it'll really kick the kicker back, and you can hit your shin and hurt your foot and these types of things. So it was similar with the car. So without electric start, the car was not something that people of, let's just say, like smaller stature, they couldn't start their own car. You need to be like in really good physical condition to start the car. So this was not going to be sustainable for all cars for all people was not the case without the starter motor. You'd have to be like cars for people who are able-bodied, or cars for people who have enough money to carry with them a chauffeur mechanic and tell them, hey, get out there and start it. You keep your chauffeur mechanic in the back of the car just so that he, assuming most likely, could start the car for you. It was kind of crazy. Yeah, trunk monkey like that guy. So then they came up with, the electric starter, and I used to actually remember who came up with it. I don't recall right now. It was a pretty good one. Yeah, I'll remember randomly, right? But this is the direction we were trying to go, and so you can see there was an urgent need for this type of thing. So remember, the starting system, all it really does, it provides a method of rotating or cranking the vehicle's internal combustion engine to begin the combustion cycle, right? You can't begin that unless you turn it over. Now, generally, the overview would be the battery. That was last week. High and low amperage wires, so that's kind of been this whole semester. A solenoid, which now we're into starting system. So the starter itself has the solenoid on a modern vehicle, and then the starter motor assembly, the ring gear, and an ignition switch. All right, so when we go to crank it, and we're going to see a diagram of this, when we go to crank it, the pinion of the starter goes out, and yes, it does engage the flywheel. That's very true. And the flywheel specifically on the outside has a ring gear, and we'll have a picture of that in a little bit. So the starter is going to engage the flywheel and spin and engage the teeth on the outside of the flywheel, which we call the flywheel ring gear, and then it's going to actually start turning that engine. That's the lot of words version of what's happening here. Pictures are better, so we'll get to pictures. But just to discuss a little bit more about the starter motor. So if we were to say starter motor specifically, this part is the part of the starter motor. So sometimes you'd be like, I need a starter. That probably means starter motor, but this specifically is the motor, this black part right here. Then on this other style, this part is the starter motor. You can see, so this is an electric motor right here. And that's, a critical part of the starter. This one has a solenoid on the side of it. This one has a solenoid kind of built in, so they can vary. But in the most basic, if we were to look at this starter motor, it's really similar to a lot of different electric motors. And this is usually people's first exposure to electric motors. So we're going to start real simple, real basic right here, so you guys understand all of what has to happen inside of a motor. And then the textbook gets maybe a little more involved than they need to. So I'm going to help try to clarify the different types of starters and kind of how they work, but not so in depth where it's like you're a starter motor engineer, but more just knowing enough so that you can kind of understand the failures and what we diagnose and how we diagnose it. So here's your starter motor. Electric motor mounted to the engine block or the transmission. So that's bolted like this. It's bolted right up. Boom. Which is an interesting point, because if you look where this is going to bolt to, let's say, the block or the transmission case, this is bare metal, and the transmission case or the block is bare metal. So the ground point is made actually right there in the housing. So there is no ground wire that goes to a starter, typically.
So you were looking for who invented this?
Yeah, who was it?
Charles Franklin Kettering.
Kettering, yeah, that's right. And he had some interesting quotes. So he came up with the electric starter, that's right. He's got a few famous quotes. If you look up his name and say famous quote by Charles Kettering. Okay, so here on this starter motor, I'd like to give a quick overview. It's powered by the 12-volt battery. So our battery, as you'll recall from last week, this thing has a certain amount of cranking ability, cold cranking amps or cranking amps. So the starter is going to be powered by this directly. Everything the starter does is going to be dependent on how much power the battery can give, right? And that's why you got to know quite a bit about the battery to diagnose the starting problem. But if we were to just do a really basic diagram right here, you guys can see this. We've run ground over to here on the north, and then we've run positive over to here on the south. But you see this switch right here? If the switch was open, you guys understand there's no flow, right? So as soon as we close the switch, let's say we go with conventional electron theory, electrons are going to leave the battery. And this starter right here doesn't have a lot of internal resistance. So if you look at Ohm's law, this is going to have 12.6 volts. And it's going to have very low resistance. So you're going to have really a lot of amps. Make sense? So if you were to do the math, you might see 100 or 200 amps going to this starter. A lot. Not like a 10 amp fuse. Like a 100 plus, maybe even 200 amp cable like this big. A lot of amps are going to go through here. Exactly, because we need it. Remember how we were saying, the old school crank method, you had to be in good shape to actually start it. If you weren't that strong, you weren't starting the car. If your starter is not that strong, or if your battery is not that strong, it's not going to start the car. So we need a whole lot of amps. So if you think of power, picture a person. If the person's pretty big and they look pretty strong, they can probably make a lot of power, right? They have a lot of power. Well, electrically, power is volts times amps. We're only working with 12.6 volts. So the way we make more power isn't to increase the voltage. That's kind of a fixed number, a maximum. We're going to increase the amps. So lots and lots of amps are going to flow right here to make more power. So the electrons leave, and then I want to show you something. They're going to go right here to this thing, and this little block right here is actually a brush. And this brush is riding on this thing called a commutator. And when we send it through this coil of wire right here, it's going to actually make a magnetic field. And if we make a magnetic field such as this, we're going to have, how opposites attract and likes repel? So we're going to use that magnetic properties, and we're going to basically have this part right here where we make it into an electromagnet. If we positive this side and then through this coil is the load, right? This coil of wire right here becomes the load. At the end of the load, it becomes a ground, and we connect that to ground. We basically would induce magnetism. We'd make a magnetic field. But the thing is, like in this one, for example, this is a permanent magnet motor. There's already existing magnets right here. So if we make a magnetic field, and let's just say we do like right here, you see how if it's spinning clockwise, it's starting to come up to the north? Well, let's just say we magnetize this to be a south, and this is a north. What's the south going to do in relation to the north? They're attracted, right? Boom. Then once they get up to that level, you know what we'll do? We'll switch them. And if we make this a north and this a north, what's it going to do? Repel. Boom, it's going to push it over here. But then likewise, we're doing the equal but opposite on this side. So if we send the positive right here and see the south is coming down here and it's just about to the south. So I'm going to say right now, we're probably going to make this one like a north. And this one's a south, and that's all it ever is. It's going to attract, and then right at the instant that it goes to pass, it's going to switch real quick. Now, how it switches has to do with this thing right here, and there's a better picture a little bit later. This is like the commutator only has one split in it. So this is when this one would be a north-north, and then when this spins around, this one would be a south, and it'd be right there. So this is just like in half. So if you think about it, we need it to switch. North-south, south-north, north-south, south-north. We need to keep switching back and forth. That's kind of hard to do. So we just literally run the positive to this little brush right here, which literally touches this commutator and it drags across the surface. And as the commutator spins, you see the split in it? That split, when it goes from this piece to this piece, that's going to change it from south-south to north-south, and that's going to make it repel. Make sense? Or actually I have it the other way. It's going to be south-north right now, but once it hits here, it's going to be south-south, which will make it repel. Kind of sort of makes sense, just a little bit. Just for a basic introductory, you need to understand we're sending positive and negative to these, and that's going to make a magnetic field that's going to attract or repel, and then it's going to switch. And then it's going to switch, and then it's going to switch, and then it's going to switch, and then it's going to switch. So right here, you just have one section. Now, in reality, as we get in there a little bit later, this wouldn't make really a whole ton of torque because, you know, there's a big gap between when it's repelling and when it's attracting. So we're actually going to slice this up a bunch more times and make it switch back and forth between north and south a lot more frequently. And that's going to give that motor, you know, like more torque and more consistent, more smooth power delivery. Cool. So this is just an example of the single loop. There's going to be many, many loops. You got to sort of understand the concept of the single loop, or the multiple loops. You'll be like, what the heck is that? What is happening there? Cool. All right. So if we were to take a look, let's just say we had this right here. This brush is worn off, like it's gone. If we were to send positive to a brush, but the brush were to not make the contact, would this make its magnetic field? No. Starter's no good. Starter's no good for us actually means replace the starter, but you know, to take it to like the next level would be like, oh, let me look into it a little bit more. Is the starter getting the 12 volts? And if it is the 12 volts passing through the brush and into the commutator? And then you find, oh, the brush is worn out. How would you fix that? Replace the brush. Yeah, but we don't do that. But in some places they do that. And so if you could go back, this is even way before my time, but back in the day, if a car came in, it had a bad starter, cool, you'd diagnose it as a starter, you'd take the starter out, you'd disassemble it, you'd replace the brushes, you'd clean it up or whatever, and you'd refurbish your own starter. Would you like to do that? That would be kind of fun, I think. All right, so if we're going to refurbish our own starters, that means you need to know just a little bit more than, oh, it's a bad starter, right? So we're going to go at it as if someday starter remanufacturing is going to return, but don't count on it. It's probably not going to, but I still want you to know a little bit more. Now, the second we give this our positive and our negative, it's going to do the attract and then the repel. Make sense? But we're going to take this shaft and we're going to attach it to like a gear. Like if you guys can see this gear right here. and we're going to make that gear turn the flywheel. Makes sense? It turns the outside of the flywheel, and the flywheel is going to turn the crankshaft. So the second it gets the power, if you will, the power, that's going to spin and actually turn the engine. Then when you're done, you remember how you turn the key and you go to start the car, right? You hold it in the crank position, and it goes sha-na-na-na-na-na-na-na. When it started, what do? I had a neighbor that lived across the street from me when I was a kid, and they would hold that sucker right in there. And it'd be like, and then they'd finally let it go. And I was like, what are they doing over there? Yeah, and they would kill starters all the time because they were holding it too long, right? But you guys know by the time it starts, your engine wants to turn really fast. You let go of the key and the starter will retract. And then the engine's off and running and your starter's back to doing nothing. Make sense? Just waiting for the next time. Cool? Right, so as we get more into it, you guys can see, remember this battery stores chemical energy. So we're storing chemical energy, and when we want the engine to run, we need more like a motion kind of like this. So this is a device that will take the chemical energy and transfer it into this. So if you think about that, chemical energy becomes electromotive force. We send that to a motor. The motor utilizes magnetism, and then once it utilizes the magnetism, it's actually going to spin the engine over. So it's pretty cool. Rather than the human eating peanut butter and jellies and then doing this, it's kind of replicating that, but it's not as big, and you don't have to like pay it and feed it and stuff. You just leave it in there. It'll work for you when you're ready. Okay, but there's just a bit more to it than that. So like if we look at the electric motor, the drive mechanism, and the solenoid, those are all parts of this. So we talked about the motor, but there's more than just the motor in here. So we'll get into the solenoid and the drive mechanism too, a little bit more in depth on those. Okay, and you guys can see from here to here, if you notice, the starter motor is turned. So when we sent the positive here, it started to pull this over, and as it continues, look, can you tell how it's rotated? It's rotated like 90 degrees. Right there, you can see that brush is making a south-north. The second this brush changes over, you guys can see the positive is no longer going to be going to this loop. The positive is going to jump to this section of the commutator, and instead it's going to make this the south. Make sense? You guys kind of see how it switches the magnetism now? This is going to rotate, and once it jumps into that segment, it's going to make this one a south, and this one, if you look, is powered by this commutator. Well, that segment's about to jump up, and it's going to get the ground side, which will make this one into a north. So right now we have north-south, but in another just couple millimeters, we're going to have a south-north, which will again, if it's south-north, that's going to repel off of this magnet, and then this magnet is going to attract, and it'll just keep switching and switching and switching.
Paul?
Uh-huh.
The way you explain it, I think it's easier if you use Fleming's left-hand rule.
Okay, shoot it, because I have no idea what you're talking about.
Fleming's left-hand rule, if you have a magnetic field,
Okay.
direction of the current, if you put your fingers like that, force magnetic field current.
Okay.
If you orientate the magnetic field direction
Yeah.
and the direction of the current, which is like this,
Okay.
the force is going down that way.
Okay.
See that?
I don't totally understand what you just said.
Force,
Okay.
field,
Force,
current.
field, current. Okay.
Okay, so your magnetic field is going this way. It's horizontal, right?
No, I don't get it.
What direction is your magnetic field going? North to south is going this way. It's
Okay.
horizontal,
Okay.
right?
Okay.
So you put your finger that way, this way,
Okay.
right? What direction is your current going? That way, into the paper,
Okay.
right?
Okay.
This is the resultant force. Down.
Okay.
See?
I see.
It's turning
Okay.
clockwise. You see that?
Yeah.
Yeah, Fleming's left-hand rule.
Fleming's left. I'm gonna make a note, and I bet you there's a pretty cool animation on it,
Force,
and I'll add it.
field, current. For motors.
Yeah.
For generators,
Yeah.
it's the opposite.
Right hand rule.
Right hand rule.
Oh, okay.
Because generators, you are using force and field to generate current. Whereas in a motor, you're using force and field field and current to generate a force.
Okay. I want to study that a little bit more with you, but I get what you're saying. I'd like to even show an animation on that, but if I do, it'll be like copyright claim. So I'll hold on that, and then I'll link in. I guarantee somebody's done a pretty cool animation on that. I haven't heard of that, so that was really good input.
Yeah, because if you're trying to look at it like that, you could figure it out. But sometimes it gets confusing because you don't know what direction the current is going.
And like from a technician perspective, you know, we wouldn't take this apart and be like, okay, which direction is this going to go, so much as if an engineer designed this and the car's in the shop, you know, the customer's never going to say like, hey, if I sent positive on this shoe and then positive on this brush and then negative on this brush, which way would it go? They're more going to say, I turn the starter and it goes click. And then if we were to look into this, you know, you might say, overall, here are the wear items. You know, we could have an issue with the battery. We can have an issue with the terminal. We could have an issue with the switch. We could have an issue with this cable. Or once it gets into the starter, you know, we want to make sure we know, is it in the starter? Because we're going to replace the starter. Is it in the cable? Because we don't want to replace the starter if it's the cable. Is it the battery? Because we don't want to replace the starter if it's the battery, right? But if you really want to go a step further, you kind of want to know what's happening in here. So if you were to look at, let's just say, you know, this is a winding, or they'll call it a looped conductor. Do you guys think there's any possibility that this looped conductor is like kind of like a bare wire could fail? It could, and if that's the case, you know, we would definitely need a starter. But mostly from the technician perspective is we want to make sure that it's inside of here, and if it's inside of the starter, we're probably just going to replace the starter type of thing. So how would we check that? Well, if we have 12 volts coming in at this point and ground at this point, and we verify it's got good 12 volts and it doesn't have a voltage drop, and it's got good ground, it doesn't have a voltage drop, then it's in the starter, we're pretty good. But we'll still take it up to another level just so you can understand really in detail. So here's where the starter lives. Transmission or transaxle right here, engine right here. A lot of times the starter's right where the two combine, right? Because your transmission or transaxle has this bell housing, and that's what houses the flywheel. And if it's an automatic, that's also what houses the torque converter. But if it's a manual, that's where the clutch lives. So because that's where the flywheel, or technically flex plate, if it's an auto, lives, we need to have the starter here. Because remember, that starter gear needs to contact that ring gear on the flex plate of the flywheel. So it lives right there. Now if you look a little more detail, you see this big heavy looking harness right here. That's going to be the big positive cable that goes there. You guys will recall a little summary. Where's the ground wire?
On the bottom?
There is none. It's the case, exactly. So all we're worried about is this big positive. And then there's one other small wire we're going to be worried about, but actually checking to see if a starter's getting what it needs is not very complex, although sometimes hard to reach. All right, so here's the overall diagram. This won't be the first time that you see a diagram like this, or it won't be the last time, I mean. Here's your big positive. This is the fat wire. This is like the 4 gauge or the 2 gauge, or sometimes even bigger, coming over right off the battery, going straight to the starter. So why doesn't the starter run all the time?
To the switch.
Yeah, but it does get big power all the time, but we also needed to get this little, sometimes I'll call it the little wire. The little wire needs to trigger the solenoid, okay? So if you understand this diagram, when we get in the solenoid, you'll kind of understand the solenoid a little bit better. So we start here, 12 volts is going here all the time, period. That's the big cable. Then from there, we're gonna, fuse, go to the ignition switch. You guys see the ignition switch? Why does the starter not run right now? Yeah, it's unlocked. So the key's off. What if I turned it to accessory? Still won't start. What if I turn it to on? That's ignition on. right? If you were to turn it to ignition on, you could go out there and you could hand crank it and it would start. But to actually make the starter run, you guys see you have to connect it to the start position of the switch, right? That's why your starter doesn't work until you go all the way forward. Or if it's a push button system, that's why when you press the button, it doesn't work until you put your foot on the brake, and then it sends the signal to actually mimic kind of like the start position. Then if you look, the start position goes to this relay. And then right here is where it gets a little bit vehicle specific. So on this one, we give 12 volts to the starter relay, but see right here, to make a magnetism, what has to be available here? We would need to get ground, and where's the ground come from? Can you tell? In this case, we have a computer that's going to give it ground. If it was more simple, we would just provide a ground right there. But you know how I said my neighbor likes to hold the starter too long and it would kill starters? Well, we're going to give the ECU some control over that. So when the ECU sees, 800 RPMs, it's like, hey, take the ground away. If the ECU took the ground away, that would stop this from magnetizing. That would shut the starter off so they can't continue to grind the starter up into the flywheel. Make sense? So on an old car, there was no ECU. But on anything like starting in 2000 or a little bit after, the ECU is going to have a little bit to say on the starter operation. Make sense? However, even if the ECU or no ECU grounds it, that's going to magnetize this, which what's going to happen to the switch side of the relay? Click. Okay? So if it goes click, we have 12 volts now that passes through, and 12 volt goes to this thing. And what's this thing? We just had a little chat about this. All right, so this is a switch that's in the transmission. When can the car... Kind of. In this case, it's just a neutral safety switch. So what positions will it start in? Park and neutral, and that's it. Now, once in a while, those switches fail, and they may not start in park. So one of the things I'll do is I'll pull it in neutral. And if it starts in neutral, but it doesn't start in park, I know I got a problem in this area. Make sense? So park and neutral are safe. If you have the car in drive, it's not going to start. It shouldn't start. If we hear another story like we did earlier, I'm just letting you know, someone took this and they took a wire right here and they ran it around the switch and they bypassed the switch, and now it will start in drive, first, reverse, whatever. That's like somebody bypassed the safety mechanism. Make sense? So this is an important part in the starting system. But let's say you are in fact in park or neutral, then the 12 volts will pass through, then the 12 volts will activate the solenoid. In a little bit I got a diagram of a solenoid that'll help you really visualize it, but the basic is for now, if I send 12 volts to this wire and there's no 12 volts on the little wire, this thing does nothing. Yes, we have voltage available to the starter motor, but we need voltage on the small wire to actually activate the solenoid, which is then going to do two things: kick this starter gear out like this into the flywheel, and also make an internal connection electrically so it'll spin the motor. We need both of those. So let's say a car doesn't start. Could it be a problem on this big wire? It could. But could it also be a problem on the small wire? Or the switch? Or the relay? Or something over here which grounds the relay? Or something in here which is the ignition switch, right? So it could be a number of different things. Make sense?
Or the connection of the motor too, right?
Sure, if you didn't have that small wire connected, no good. Mainly, if we have an issue on this big one, it's usually like, I would suspect more the starter would work, but it might not crank very well, because this is a big wire right here. This big wire doesn't easily get cut or chewed, and it doesn't have connectors. It's got like a nut and bolt, like it's a big, it's bolted on. So we don't usually see connection issues there that cause like an open. But if we had high resistance at the terminal, if we had high resistance at the eyelet where it bolts to the starter, that would cause a voltage drop, which would generally cause the starter not to crank as fast or as strong, right? But usually if the starter's not cranking at all, we're probably more concerned about this or the solenoid itself. Kind of makes sense? So we'll get a little more into how we would diagnose it. But let's just say it was a manual transmission. What changed right there? Did you guys see the change? Okay. Right. So if it's a manual, there is no park, which
It's neutral.
I like that. Very good. Yes, but there's no switch to know that the transmission's in neutral. So what they'll do, they'll put a switch on the pedal, on the clutch pedal. So the only way to start a manual, you got to push your clutch pedal down.
So that's the stick.
Yeah, exactly. Stick shift. Exactly. Stick shift manual transmission. I really don't call it standard because the reason we used to call it standard, you guys have heard of it called standard? You got a standard? That's because like in the 70s, 60s, 50s, 40s, 30s, when you rolled into the dealer and you're like, hey, I want to buy a new car. And they're like, do you want the optional automatic or do you want the standard manual? So they'd say, I want the standard. I don't want to pay the upgrade fee. I want the standard. Standard is just a term that means like you're not paying an upgrade. Make sense? Back in the day, all cars were manual. That was the standard. An automatic was optional. Make sense? So manual, stick shift's fine. Standard is okay, but it's just a little confusing because now the automatic is standard. So if you roll in and you just say, hey, I'd like to buy a, you pick it, Tacoma, I don't know, whatever. Trust me, they're going to pull an automatic transmission vehicle around the corner. You'd be like, wait a minute, I want it with a manual. And be like, what? We don't even have those in stock. We don't sell like hardly any of those. Make sense? So standard I'd get away from if you listen to me. That's what I would do. All right, so let's just say similar components. However, if you go to look at this coil side of the relay, we don't typically use the computer in this case anymore because and a manual, it's a little more like old school. You know, we're not really using the computer. That's one of the reasons that it's hard to include the latest and greatest computer assist features in a manual because the computer doesn't work really well with a manual. The computer can't press the clutch for you. Whereas in an automatic, the computer can shut off power to shift solenoids and make it neutral for you. Kind of makes sense? So if you look at this, if this gets 12 volts because we're in the start position, cool. This needs to get ground, right? How does it get ground? Can you tell? Ground right here. You have to press the clutch pedal down and that will close the clutch start switch. Now this is a kind of a cool example because on some of the like Nissan and Toyota trucks actually had this. There was in some of them this clutch start cancel switch. So if for some reason, let's say there you were off-roading, whatever, in some Mount Fuji or something, and you came up to this cliffside and you're like, whoa, the cliff, boom, and you stop, and let's say you stall it and you're teetering on the edge. You're teetering on the edge. Your front wheels are about to go off of Mount Fuji. You'd probably want to start it and put it in reverse, right? But you got to take your foot and put on the brake, then you got to take your left foot and put on the clutch, and then you got to kind of get in reverse and you got to feather the clutch. How about this? Put the transmission in reverse. Don't even depress the clutch, and you can actually press this clutch cancel switch and crank it over. The starter will turn the engine. Because you're in reverse and your clutch is out, the engine will actually turn the transmission and it'll slowly just back you up safely so you don't roll off the edge of Mount Fuji. Cool. So this is a pretty cool little feature in some of the trucks, but it's rare. Most of the time, none of this is here. It's just the clutch start switch right here. So let me make sure you guys understand why this is here. A different school, not this one, had a student who pulled in. It's always a Nissan 240 if it's a bad story. You guys know about those little drift cars, okay? Nissan 240 came in all sorts of clapped out. Just, you know what that means, right? Just had a lot of people work on it, had a million different owners, just a lot of issues over the years. What'd you say? No, a Nissan, a little like a 90 Nissan, you know, engine swapped drift car with an engine swap that was done by somebody who didn't really, not real professional, right? So they put the engine in, it wouldn't start. They ended up diagnosed it as a bad clutch switch. So they took a wire and they bypassed the clutch switch. And, you know, whatever, it's their car, right? My car, my rules, don't tell me what to do. Well, this is the problem. They pulled it into the school to do compression test practice that day. And so they had 4 different people working on it. And the owner of the car was out there with the compression gauge and they said, hey, will you crank it? We need to get a compression number. The other student reached in, grabbed the key, turned it, and what do you think happened? It rolled, it was in first, and it rolled forward and pinned somebody up against the toolbox. So the reason that this is here is so you can't try to start it in gear. You have to have the clutch pedal down. This student wasn't familiar with how a manual worked. Didn't happen to realize, it had a shifter sitting here like this, and was, sometimes they'll call it the Gen Z anti-theft device. Was unfamiliar with this Gen Z anti-theft device, so didn't even realize it needed to get in and push the clutch, but it was bypassed. So boom. So that's why this exists. Make sense? Now, if you had a no start on a manual, it's very possible that we could have an issue with the clutch switch. The way we would test it is the clutch switch gives ground, right? So if the clutch switch is getting ground, you push the pedal down, it should be giving ground to the relay. But if right here you still have 12 volts and your clutch pedal's depressed and you have ground right here, you know that this clutch switch it's no good, exactly. Right? So that's one of the things that we might have to diagnose. Cool. Now, this is the solenoid picture. I want to make sure you guys understand really well. And then we're going to look at a solenoid diagram too. So you see this big positive cable? That big positive, I'm going to use this starter now because the solenoid's off to the side. The big positive goes to here. Make sense? That means this gets 12 volts all the time, all day, every day. It's connected directly to the battery, period. Could it have some corrosion and issues? Yes. But we can check that. That's one of the later tests, is like starter cable voltage drop testing. So this big one gets 12 volts all the time. Then if you look, you see this little strap right here? On this one, it's like a little copper wire. That's the one that actually powers the motor. Make sense? So you having 12 volts here doesn't mean you have 12 volts coming out here, right? 12 volts comes in from the battery, and then right here, this doesn't get 12 volts until, did anybody know what has to happen? Yeah, we got to put power on the small wire, which goes to the solenoid. See this little wire right here? When this little wire has 12 volts, it connects this to this. And if this is connected to this, look, the electricity is going to go right into the motor and make it spin. But the solenoid does two jobs. When it gets the small 12 volts here and it's grounded at the case, that's going to magnetize the solenoid and kick the gear out. It's going to kick the gear out into the flywheel. But also, when it kicks it out, that solenoid's going to touch like this, and that's going to connect this to this and make it spin. Make sense? Make that magnetism occur, and make the opposites attract and the likes repel and spin. Cool? So if you were to look at this one, this big power has power all the time. If we want this starter to actually run, we got to give power on this little terminal right here. You want to see where that terminal comes into play? Back it up one. This is the small wire right here. The small wire goes through all this stuff, and then it goes to right here. That's the small wire on the solenoid. This is the big wire. Make sense? On your typical starter, there's only two. If it's an automatic, this going through all this stuff is the small wire. The big wire is still the same. Make sense? So let's say that here you are diagnosing a no crank, no start. You think it's got a bad starter. Cool, we need to verify that. Does it have 12 volts here? Yes. Does it have 12 volts here? How would you even check that? I'll give you a clue. If we looked in this diagram, what do we have to have happen to have 12 volts way down here at the small wire? Somebody needs to be holding it in the start position. And then when someone's holding it in the start position, you need to see, is there 12 volts making it to the small wire? If there's not, let me make sure you understand what that looks like. If there's not 12 volts on this small wire while somebody's turning it, you know what that means?
It's no good.
Something's no good. I'll tell you what, I'll make it even more simple. What if there is 12 volts right there and there is 12 volts right here and the starter doesn't work? You could bang on it, whatever, but from a regular flat rate, modern day, even hourly, current 2025-ish or so technician, we're done. This starter has the 12 volts, this big 12 volts, it's getting its signal. And then if the starter's not working, then it's no good. Get a new starter, put the new starter in. But I want to try to teach to a little bit of a higher level than that, because Tim said is correct. If this has 12 volts and this has 12 volts, but the starter doesn't run, you need to determine, is the solenoid clicking, right? So if this gets 12 volts, the solenoid should click. If the solenoid doesn't seem to really be kicking the starter out and moving, the solenoid would be no good. And then if the solenoid is kicking out, but it's not making the motor turn, then I would suspect there's a problem in the motor, right? So back in the day, you used to have to separate was it the solenoid or was it the motor? So like what I've seen some old school people do, they'll take a screwdriver and they'll put a screwdriver here and they'll like touch the screwdriver here and that'll bypass the solenoid. And if the starter goes zing, you know that the starter motor is good, but it's a solenoid that's bad. See how that's kind of backyard janky business? But it's effective. It's scary though, I'm not gonna lie. That's pretty sketchy. There will be sparks, there will be glowing screwdriver metal parts and stuff like that. So that'd be janky. The real way to do it would be make sure it has 12 volts. Make sure it has 12 volts. If it has 12 volts and it doesn't click, we know it's the solenoid. There's no real way to guarantee that it's the starter motor because the starter motor won't work unless the solenoid works, and that's where the screwdriver janky business comes in. Make sense? But let's say it's the other way around. You have 12 volts here, but you have no 12 volts here. Why wouldn't 12 volts be making it here if you're in the crank position? Then we got to look at the diagram. So if you look at this diagram, if there's no 12 volts here, it could be this wire, it could be this relay, it could be this contact in the relay, it could be the magnetization part of the relay, it could be this clutch switch, it could be that ignition switch, it could be this wire, it could be this fusible link, right? So see how you'd have to do more diagnosis. In a way, what you hope is that it has 12 volts right there, and then you're like, needs a starter, my job is done here. Then of course you get a starter from AutoZone, you put it in, it still doesn't start, and then you're like, oh, check it again. If it still has 12 volts and it still has 12 volts, doesn't matter that it's a new starter, that starter is no good, makes sense? And this is stuff that happens on a daily basis for people. So I don't want you guys to be like, well, I put a starter in, and if that doesn't fix it, then it's gotta be something else, because sometimes a new starter is probably realistically a remanufactured starter. Do you really trust the remanufacturing process? Are you really sure the remanufacturing process is good? Andy, I'm gonna give you a chair, but you gotta come get it. And this chair is kind of sketchy, so be careful with that one. All right, so knowing this is gonna be really critical for you to diagnose, and that's where we're gonna put most of our effort, but we'll still go a little bit more into the starter because there are several different types. So like, for example, your gear reduction starter, this is not gear reduction. If you look, this is direct drive right to the starter. You see how big this thing is? This has a lot of power. This pulls a lot of amps. So go ahead.
What does the ST stand for?
Start. Actually, just start, yeah.
Okay.
Here's a gear reduction starter. Can you guys see the difference in size? Can you tell the difference in weight? No, because I'm holding them. But if I hand them to you, you'll know. This was a big chunky beast. Back in the day on old cars, that would be fine. On a new car, we don't want that big. We don't have room for that. So with this one, this motor makes a lot less power. Can you tell? It's smaller. But it makes similar amount of torque because there's a little gear reduction unit in here. So this starter spins faster, but it has a gear train that's going to triple the torque and end up making just as much torque as that and sometimes more. So this is the gear reduction starter, which is normal. Right, so if we were to look at it, we've got the big battery terminal going to the solenoid. We've got the small wire, which is shown here actually. Big power to here, small wire to here. If we get the small wire to have power on it, it's actually going to magnetize this and throw it over. And you can see that this is a coil that's designed to actually do that motion, boom, like this. It doesn't make it spin, it goes like this, boom, boom, boom. That's all it does. Then you can see there's a couple different gears right here. And then that's gonna go out to the actual starter gear, which will engage the flywheel. So right here, it's just saying, like in this case, current flow is gonna go battery, ignition switch, terminal 50, which goes to the hold-in and the pull-in coil. So this one gets in detailed. But if you look, here's the difference. Engaging, you guys can see, it's actually gonna move this solenoid over, which is gonna connect the big battery power right here. They call it 30 to C. And you're like, what the heck? This is Toyota specific numbers. Not every car uses these numbers and letters and stuff, but what I can show you for sure, this one shows it better. Remember this one, We send power to this all the time. When does it transfer power down to this one and go to the motor? Do you remember? When the solenoid kicks, so that's what it's showing. When the solenoid kicks over, terminal 30 is connected to terminal C. Make sense? Terminal 30 goes through a contact plate. The contact plate's inside here. If the contact plate were to be messed up or corroded or something, the voltage at 30 would die at the contact plate. It would never go to C, and the starter wouldn't do its it wouldn't do that. Make sense? So that would actually be a failure of the solenoid. The solenoid not only does the chung, right? It does that, but when it does that, there's a contact plate right here. You can see it's going to make contact. See that contact right there? Now you don't, right? So look at that solenoid, how it's pulled out. Boom, now it's in, out, in, out, in, out, in. That has to be in good condition. If it's in bad condition, the electricity is never going to make it to terminal C, and terminal C is what brings it up to the motor and makes the actual magnetic movement. See why we started with the basic magnetic movement first? If you don't have 12 volts going to that electromagnet and ground coming out of that other electromagnet, that starter's not going to do its rotation. Make sense? So this is a good example of the solenoid. And you can see when the solenoid throws, it's going to actually spin the starter, and that's going to pass the torque through to the flywheel, as you can see. Make sense? You guys can see how it moved out, right? We focused on right here. What if you focus on over here? Out, engaged, out, engaged. Does two jobs. Cool? And then when we're done, would you agree once it's started, unlike my neighbor, you let go of the key and you can see it's going to retract back in, which is going to open this contact as well, which is going to stop the starter motor from turning. That's really what it does right there. In fact, Ron brought over this starter, and I'm thinking about using it. That'd be cool. Yeah, let's try that out. Let's see if this I've never actually seen before. I'm just looking at it. We got a jump pack, so this should be legit. If I take the jumper and I find the ground, it looks like is over here on the case. Oh, that's the positive, it's labeled. Here's the ground. Cool. A little sketchy, but I like it. Okay, right here. Now when I turn this on, what should happen?
You should hear it.
Nothing, because there's a little switch that you can't see right here, and this is going to send the signal to the actual solenoid. Okay, I like it. It's intense. So this will be kind of convenient because it does have an external solenoid. You notice the solenoid's not up here. So they do have starters that have an external solenoid, and that's something I added into the presentation. But with this one, just to show you kind of what happened here, this is how they're going to bench test it, by the way, if you bring it back to O'Reilly's or AutoZone or whatever. If you notice, we got the starter motor, but you have positive battery cable coming into this solenoid right here. This wire doesn't connect to this wire until you turn the key and it gets voltage on this wire. So that's the little wire. If I get voltage on the little wire, this big wire gets connected to this big wire and it engages the actual motor and makes it spin.
So what is the bottom called, the little one?
Solenoid.
That's the one, right?
Exactly. Yeah. And I've heard them called a lot of things. Solenoids and all sorts of stuff. You know, I've been around a little bit. I've seen some stuff. But now, so you guys know, all a solenoid really means is it's got a magnetic field and it makes movement. So like a fuel injector is a solenoid actually. An EGR solenoid, a transmission shift solenoid. If we give it 12 volts in ground, it's gonna move. Now in this case, when it moves, you understand what it does. Throws the starter into the flywheel, but also makes this contact and sends current into the motor. Make sense? For cranking, that's the starter solenoid. That's mainly the click when you hear the starter. Like when you go to crank the starter, and sometimes, have you guys ever seen a car where you go to crank it and it just goes like, not a little click, because you might be hearing the relay and some other various relays. But ever heard one that goes kind of loud like click, click, click? That might be the solenoid actually moving, But if you had a problem in one of the windings in the motor just no turny. Makes sense? So you'd be like, hey, the solenoid sounds like it's working, but the motor won't actually turn. The actual starter motor. Cool, and that one they're separate, which is cool. And then if we look, remember we were talking about like those magnetic fields and that commutator? And to be quite honest, that's, you learn about this stuff when you're in school, and however much you learn right now, for most of us who fix cars every day, that's going to be about the extent of it. If a car comes into the shop, you never really get to do like a science experiment on one of these. So this is an area where I'm a little weak. Diagnosing the car and recommending the right part, I'm better at that. Do you know why? Because you get good with repetition, right? So when the cars come in, I diagnose it, I verify it's the starter, I sell the starter, I put the starter in. I never come out and I'm like, well, let me determine how many segments there are of this motor and how many segments of the commutator. You see what I'm saying? However, you can see, remember that commutator thing? It's right here. And here are the motors, and these are the windings. So each one of these can change back and forth, positive to negative, negative to positive, right? It'll change the what would you say, like the polarity to change the direction of motion. Kind of made sense? The left-hand rule. I'm going to so study that. You'll see.
I can explain it to you later if you want.
Yeah, but I might take a few times to really understand it, but I do want to learn it more. All right, so like here's a couple difference of starters. Overall, because we don't really want to make room for these huge monster starters, we want to mostly keep it a little smaller, get rid of this thing, and use some version of a gear reduction starter. We could use planetary gear set, we could use a spur gear, just various different types, but you'll notice the solenoid's off to the side and the actual motor is next to the solenoid, and that way we're actually going to transfer power from one side to the other and get some gear reduction here. See how they're all a little similar? This is pretty much all you're going to see, I'd expect. Rather than this one, this is a direct drive starter with an external solenoid. This is cool, but not current use.
Those you would see more like in like golf carts and stuff like that, right?
Golf carts do it. Golf carts can do it in two ways. Sometimes like a gas golf cart will use a solenoid to run the starter, but like an electric golf cart will actually use the solenoid to give power from the big battery, like a 48 volt golf cart will go through the solenoid, which will then power the motor. So yeah, they'll use external solenoids on golf carts, but they used to use it on cars too. You'd be like, oh, it's the starter motor or it's the starter solenoid. And sometimes the starter solenoid would be like up on the firewall. Whereas now they're mounted right on the starter. So really our diagnosis is easier, because just imagine if it was in the old days and you're like, is it the starter motor or is it the starter solenoid? Now you're like, I don't care. They come together. I don't know if it's the motor or the solenoid. I just know it's one of the two. And so I replace both, right? So it sounds like, we're guessing, but this is the thing. Like you only need to diagnose it as deep as getting the right part on the car and giving the customer the estimate and having it fix the car. So I'm kind of overshooting by trying to teach you the difference between the solenoid and the motor, just because, I want you to know. I want you to be like thoroughly know what you're doing, not be like, oh, I didn't learn that. Because once you're out of here, you don't really get the time to experiment with the starter solenoid versus the motor. However much you learn right now while you're studying, that's probably going to be it. Unless you go do a different career, electrical engineering, for example. You come back and teach me. Shoot it.
Does a scan, is a scanner able to pick up errors on this thing, or?
Generally, no.
No, okay.
So let's say, I'll bite on that. If you want to diagnose this, your main tool, you could use a test light, but test light's not going to tell you in detail, right? A test light's going to tell you, I have power here, but how much? I don't know, it's a bright bulb or a dim bulb, you can approximate. And I have power here or I don't, right? But with your meter, what should you have on the big terminal coming off the battery? 12, but be specific.
Opens it.
If the battery's fully charged, I agree. If you had a battery fully charged at 12.6, but you were only getting 11.6, you'd be like, hey, why am I dropping a volt on the cable? Makes sense. So our meter is going to be our diagnostic tool. And then when it comes down to checking the small wire, the wire for the solenoid, same thing. We're going to see, do we have 12 volts there? Do we 12.6? Do we have 12.1? Whatever, all those are good. But if you only have 2 volts here, you know that it's upstream in the wiring diagram somewhere. However, we could use a scan tool for some things. So if you wanted to start the car, you could turn it with the key. But remember how sometimes the computer controls too a little bit? Sometimes you could go in and command the starter relay so that you could see if the ECM is providing that ground or not. But mainly, no, the main workhorse is going to be the meter on diagnosing this.
So even
No codes.
Even in very modern, complex cars, the German high-end cars,
Nah.
it's still pretty basic as
Exactly.
as a device.
And that's why starting systems is like its own standalone thing, because you really need to understand this top to bottom and side to side. If you think that you're just going to plug a scan tool in and it's going to give you replace the starter DTC, let me know what the numbers are, because I've seen, I think, all the numbers, and I've never seen a code for that. I don't think it exists.
Okay.
I don't think they've even made accommodations for that. Now they may have, I'll sidestep it just a bit. They may have these auto start-stop systems, which we cover in a bit. Those can set codes to replace the starter just based on the number of times the starter has run, but it's not really for diagnosis. It's more like the engineers say, hey, this start-stop system is going to start and stop the car at every stoplight. This starter is going to fail. You know that, right? So let's preemptively have it set a code after 100,000 operations, in which case you'll get like a service start-stop system malfunction, and then you'll go in and it'll be like, oh, there's a DTC for replace the starter. But it's not because you're troubleshooting the starter, you're more, it's been so many starts and stops and cycles.
It's a counter, basically.
It's a counter, and that's it. It's a counter that the customer can't see, so they put it in with the scan tool so that it'll prompt a code at a time. Good question. Now the next thing is about starter engagement. See this? Remember my neighbor? I gave a hard time about my neighbor starting the starter too long. I mean, I used to hear horrific noises every morning. I'm just telling you. So the engineers are smart. They're like, hey, you know what? We know that these people are holding it in too long, and that's actually a major cause of failure for the starter. So they started putting these overrunning clutch or one-way clutches. If I try to turn this starter, you're gonna have to trust me on this. I'm trying to push down, and it's like, no, you hear that? It won't move. But if I try to push up, see how it'll move? It's got a one-way clutch. So the reason that this is really nice, you throw the starter in there, the starter gear, sometimes they'll call it Bendix, engages the flywheel, and it turns the flywheel, right? And it makes compression. Then once the spark occurs and the engine's running, the engine takes off much faster than the starter. Typically a starter may be able to crank the engine 200 RPMs, 250. When an engine starts, it's 1,000 RPMs. So the starter, if the starter's still engaged, the engine's like, hey, here you go, 1,000 RPMs, this is gonna be the ride of your life. And the starter's like, ah! And that's what I heard across the street, I'm pretty sure. So instead, we put this one-way clutch. Once the engine starts, this one-way clutch, or in this case, they have Sprags, they use all sorts of one-way clutches. When it's driving, it's locked, but once the engine's running, it'll actually compress these balls, and it'll let these two things slip, and it'll allow it to just freewheel. Then if the starter's still engaged because the customer's kind of crazy, you won't even really hear anything. It'll just shh, the engine will run and the starter will be like, wow, I'm still engaged. I'm glad this one-way clutch can spin really fast. Make sense? So it won't overspeed the starter. It won't tell the starter you're moving 1,000 RPMs today. They don't like that. Okay, kind of makes sense? Do you think this has any way that it could fail? This should lock this way. Actually, depending on what we're going to turn, let me look real quick. This should lock this way, but it should freewheel this way, okay? What type of failure could we expect? What if it didn't freewheel at all? Then when the engine was at 1,000 RPMs, it wouldn't really decouple like this. It wouldn't freewheel. It would just be stuck, and that would probably kill the starter. But what about another type of failure? You guys have used ratchets before, right? You ever had a ratchet that's supposed to freewheel this way, and then this way it should lock, but when you go to lock it, it actually skips and slips? You think this could skips and slips? This could skips and slips, in which case we replace the starter, but I want you to understand a little bit better. When you go to turn the starter, if this one-way clutch is bad, this starter gear it won't move, it'll just freewheel. And so you'll have a good solenoid, you'll have a good starter motor, you hear a noise, you'll hear it go like, shing, 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 and you're like, Now we talked a little earlier, that could be a stripped flywheel or flex plate. It could be. But it could also be a failed one-way clutch. Back in the day, they didn't have one-way clutches. So if you heard that sound, you knew the teeth were stripped out on the flywheel or the flex plate. Make sense? But now, it could be the flywheel or flex plate teeth, or it could be the bad one-way clutch. Ultimately, this is what matters. What are you selling the customer? You don't know yet. Is it the one-way clutch? Because that comes on the starter. If you get a new starter, it comes with a one-way clutch. But you know what it doesn't come with? A flywheel. So is it the flywheel or the one-way clutch? You don't know. How are you going to find out? There's multiple different ways. What if I took it out right here, and does this feel like it's locking? Yeah, interesting. It feels like it's spinning. Kind of seems to me like this one-way clutch is good. I should still, though, probably take a really good look at that flywheel. Put my flashlight in there. Sometimes you can't see it. Sometimes you can put a little borescope, endoscopic camera, take a look at the teeth, turn the flywheel over, look at all the teeth all the way around. Because the engine tends to stop in one spot on compression, and that's the spot the starter always hits. So you might be like, oh, those teeth are good. Yeah, but way over here, those teeth are like falling out. They're like hammered. What'd you say? Oh yeah, the mirror helps too. Yeah. So see, the cool thing about working on cars is if you understand the concept, you may come up with a better idea than what I have. Back in my time, cameras weren't really that big of a thing. So like I got the first borescope camera, and it was like a lens and this flexible tube, and I'd be like, oh yeah, those teeth look good, but I couldn't really see it very well. It also said, kind of weird, but it also said right on it, not for veterinary use. And I'm thinking like, okay, I wasn't going to do anything with that in my dogs. If they're sick, I bring them to the vet. They have their own camera to scope stuff out. Now they have scopes. Matter of fact, I have one right here, if you must know. It'll show you how much times have changed. I carry this around. This is a Bluetooth endoscopic camera that goes to my phone, and it's got a long camera I can send in, and it can go this way or it can go this way. So if I change a function, it'll use a camera on the side, or it'll use the camera out the end. I could send it down there and inspect the flywheel with my phone and take pictures and video. Makes sense? So like, things have changed. You guys may come up with an even better way. If you figure out a way to x-ray internal parts, let me know, because I'll buy in on that one. If that's like the Kickstarter or whatever, I'm down. Cool. So understanding this is in there can make it so that you don't sell the customer the wrong repair. Cool. Okay, and overall, I think this will probably be pretty good. You guys can see a basic cutaway. Like for example, this tooth right here is a little bit worn, but that would not make the starter not start the car. It might be like, oh yeah, this starter's clashed a few times. They also make the tooth what they call chamfered, so there's a bit of a 45 to help the teeth engage. Otherwise, you'd have the teeth hit the teeth like this, and it wouldn't work. So they put a little angle on there. If they hit, they should knock each other into mesh, and that should work. Right, but you can see here's the flywheel ring gear or the flex plate ring gear. So when we go ahead and we start it, we got the big 12 volts there, but once we get the small 12 volts, this solenoid should kick this over. This should engage and then make the electrical contact and turn the motor. Cool, so this is like a pretty nice cutaway. And these are all parts that are inside the starter that could fail, by the way. So the solenoid could fail. You could even have a problem with this fork right here with the one-way clutch. Now we know what the one-way clutch does. With anything related to the motor, such as brushes, commutator, we could even get into some of the windings. Like, are these field magnets or permanent magnets? Depends on the type. There's a lot of failures that can occur in a starter. So in that way, to be quite honest with you, it's kind of nice that we're not rebuilding starters all the time now. Somebody else, if they do it well, it's good. Just you take the old one out, put the new one in, and all this stuff is either new or, refurbished. Maybe not always very well though. Makes sense. So like if I roll to the auto parts store and they give me the option of new or remanufactured, I'm going to try to get the new. The only problem is sometimes the new is like $500 and the remanufactured is like $100 with a lifetime warranty. So I'm like, all right, fine, give me the remanufactured. But if you put the remanufactured in and it's no good, they're not going to pay your labor to replace it again and again and again. So it's a little bit of a, when it's DIY, you want to save the money, but when it's for a customer and it fails in a month, they're like, hey, you're going to fix my starter. It's under warranty, right? And you're like, well, yeah, the part is, but my labor is not. So you end up either eating it, charging them again, probably going to be a bad situation. Makes sense? So there is quite a bit going on there. Cool. And then here you can see a really good shot of, this is a true flywheel. The difference, just FYI, this has a friction surface for a clutch disc, whereas the flex plate doesn't. The flex plates looks a lot like this, but it's not real beefy. It doesn't have all this plate. It's just kind of like, got little holes and it's just lighter duty because there's no clutch to physically engage a flex plate. It's an automatic. It's got a torque converter, right? So if you look at this gear ratio and you were to count these and come up with a ratio, you come up with something about 17:1. And that's important because at that ratio, this starter has a lot of mechanical advantage. So basically this starter doesn't have to have an extreme amount of torque. It's gonna turn this really fast, and this is gonna be more than enough to overcome that high compression, these types of things. So there's a reason why this one's big and this one's small. Okay, it all has to do with, you guys have ridden mountain bikes, right? What if you came up to a really steep hill? What gear would you shift into? 21st? First. When you put in a first, you know how your feet pedal really fast but the bike goes really slow? Right, this turns really fast and this turns overall really slow, but it's easy for the starter to do it, okay? If we didn't have this gear ratio, the starter's job would be like really hard and we'd probably end up killing the starter more often than we need to. Okay, and then remember the freewheeling part. So when the engine starts, this sucker is trying to turn at 1,000 RPMs. Now that you can see that, if this was turning 1,000, imagine how fast this would turn. Like it has 17:1 ratio. So yes, it can make 17 times the torque with this arrangement, but also that could make this spin 17 times faster. So that if this engine starts and this is still coupled in there, that starter is going to way overspeed. It's going to overspin the starter. That's why we need either A, the teeth to become disengaged, or B, make sure it has that overrunning clutch, which is going to freewheel, and then the teeth will disengage, whenever they disengage. Not a big thing. And then on that other one we saw earlier, now you understand why they want the computer to have some say in this. Because if a customer continues to hold the key, that's not nice for this guy. It'd be like the computer says, hey, I saw 800 RPMs on the crankshaft position sensor, disengage the starter. And the starter's like, whew, thank you. I'm so glad the computer controls me now rather than the customer, because the customer's kind of crazy. They just don't know, that's all. So a nice cutaway, you guys can see there's your gear reduction. So here's your motor. Gonna turn this gear, turn that gear, and that's gonna give a lot of increased torque. And then we're going to get an even more huge increase when we engage that to the ring gear of the flywheel or flex plate. Okay, you can see where the one-way clutch, the overrunning clutch lives. There's another good shot of an overrunning clutch right there. You guys can kind of see like it all comes down to the ball and the spring. So if you're trying to spin one way, this ball is wedged. But if you try to spin the other way, see how this ball would roll back and compress this spring? And now these two are not really tightly held. That's how it overruns. Makes sense? That's what happens when the engine starts. It's actually, the starter is no longer driving the engine is dragging the starter. So it would actually overrun this right here. It would let it go, it'd release it. Assuming it's working. Cool. Now, a little bit about starters, and this gets into probably a little more detail than we need, but I'm still gonna shoot it. We can have starters that could be electromagnetic or permanent magnet. And we've gone mostly to permanent magnet, but you should be a little familiar with the differences. And so rather than all the words, I think the pictures make a little bit more sense. So right here is a permanent magnet. So these magnets in here are magnetic period. You know what a permanent magnet, you stick it to the refrigerator. That's a permanent magnet. Do you have to send power to those magnets to get them to stick to the fridge?
No.
No, so what we used to use though were these are the magnets, but for these to become magnetized, we'd actually have to send 12 volts to one side and ground to the other side. So these were electromagnets. Exactly why we use these, I tell you, I don't entirely know. But this was the norm for many, many years. It's bigger, it's chunkier, it's more complex, it's more expensive. And then when we went to the permanent magnets, yeah, maybe the magnet material could be a little expensive, but we're simplifying a lot of things. So if you guys ever hear the term of, oh, it's a permanent magnet starter, our diagnosis is identical. We don't diagnose it any different. This is going to be permanent magnets, and it's got magnets in here. This one may very well be electromagnets, but for our purpose, we still diagnose it the same. For the remanufacturers, they're probably going to diagnose it and repair it a little bit different. Kind of makes sense? Those are the main differences right there. If you look, these have pole shoes, and that's how they're going to magnetize those, what they'll call the field coils. So the field coils are the parts that will provide the magnetism to the electromagnets. And then you can see we'll have brushes on this commutator, kind of the same. Not really a super big deal. And then this one is the movable pole shoe versus fixed pole shoe. So this is a movable pole shoe, and I want to just skip the movable pole shoe is direct drive. It eliminates the starter solenoid. So like this one, for example, would be a little bit more like the movable pole shoe. Think of how I'm gonna get my camera out of here. This one, it's kind of interesting. When we started this one, did you notice it did kick the gear out? You guys saw that the gear kicked out? If the gear kicks out like this and the solenoid's down here, how the heck did it kick out? And that's just a difference in the starter design. We'll actually use that movable pole shoe. If you see right here, if this gets magnetized down, look, you can see that gear engaged. So once we magnetize this motor, it's got a movable pole shoe and it throws that gear out. Whereas like, you know, and that was good. It does eliminate the need of a solenoid, but we're still using a solenoid to give power to it. But on this modern one, this solenoid, it doesn't have a movable pole shoe. The solenoid is actually going to use the fork and throw the gear out. So just different types. This one's actually pretty old school here. So you may hear some of these terms. Okay. And then generally, if we were to summarize some of what this does, because we turn the key, if you'll remember, we turn the key, right? The starter relay contacts allows the large electric current to flow from the battery to the starter motor, and one of the pole shoes gets pulled into position by the magnetic field, right? That's what we were showing you right here. Turn the key, that's going to pull it into contact, okay? And that's going to make the pinion gear move into position to engage the ring gear, like you saw that, right? Which is also going to close a set of contacts, just like this. Ready? Here you go. Click. If you look, you see this little part right here? That touches this contact. That's an actual contact right there. When it does, that's what's going to send the electrons through the actual motor. So it's, again, a little bit of a different thing. And then if it's more modern and it used the fixed pole shoe, that'd be something a little bit more like this, or even probably more like this. It's going to be similar, except it doesn't use the pole shoe. It's just going to use the solenoid to kick it over. Okay, so how do we diagnose it? Kind of the same. But so you know the difference in types, just to be really thorough. So then on the new stuff, remember, we're using permanent magnet motors. So lighter, more compact, less amperage, and they're gear reduction starters. They don't require electrical current to produce a magnetic field, so it's just better. You know, I don't know of any negatives. Who would want this when you can have this, and this can make just as much torque with without using all the amps, without adding all the weight. So let's say you had, who's into hot rods? I saw some people. Ronnie, at least you, I know. If you had your small block Chevy and it had one of these, you could get rid of this and actually, they make them where it looks like this. And you're like, I want to put one of those mini starters in there. And you're like, what the heck? It's got to be worse, right? But actually, this is just a better design.
That's what I have now.
Yeah, it makes sense. The only thing is, maybe this doesn't have quite as many rebuildable components, but we're not really rebuilding those anyway. These are harder to work on, I'll tell you that. Then this old school thing was actually pretty easy, but we're not really working on them. Anyway, if it changes, I'll adapt to. All right, cool. So I think overall you should be probably pretty decent on the different types. And then as a cutaway right here, you guys can see this one has the solenoid, and the motor is a gear reduction. It's offset like that. Cool. This part they'll call the armature. So the armature is the part that spins. So if these have permanent magnets out here, this is the part, let's say that we were to do a positive and a negative, that maybe would make them attract, and then a negative and a positive would make them repel, and a positive negative, right? So this is where we do the magnetic field that's going to interact with these permanent magnets. These permanent magnets are magnetic all the time. What we need to do is switch these. Positive, negative, negative, positive, positive, negative. And how we do that, you see this thing over here. That's the commutator, and we got the brushes running on it. So if we send positive on this wire all the time, and we send negative on this wire all the time, this commutator's job is going to switch. Positive, negative, negative, positive, positive, negative, negative, positive. So that's going to do the attract, repel, attract, repel, attract, repel. Some of the reason I like to make sure we cover that is this is pretty standard, but if you get into some of the more modern motors, they'll call it like an electrically commutated motor, and you're like, what? This is the commutator, it switches positive and negative. They can eliminate all this, and remember what rides on the commutator? You remember what rides on there, kind of, or no?
Brush.
The brushes, and the brushes are a major failure point. So the brushes ride on there, and they wear, and they wear, and they wear, and they wear. If the brush is riding on this and it's spinning, don't you think they're going to wear? So what if we could get rid of brushes? What would you call the motor?
Brushless.
Ooh, that sounds good, doesn't it? And if you want to do a brushless motor, no problem. But if you don't have brushes in a commutator, how are you going to switch positive, negative, negative, positive, positive, negative? You could do it electrically. So they'll do an electrically commutated motor that has no brushes and it's brushless. As far as I know, they're not doing it on starters, but they're doing a lot on power tools, aren't you? Where are the Milwaukee fans at? There you go. Right, so at least you can visualize. There's just a little bit, this is more simple, but a little bit chunkier. If you wanted a smaller motor, you could go brushless, but you have to electronically commutate it. But the other thing is, those brushes tend to make little sparks. And that's fine on this. This is good. This is all enclosed. But if you wanted to use power tools in like a confined space inside of like a big fuel tank or something, you better not have any sparks. So you could get rid of all this stuff and make no sparks. It's actually normal to have a little bit of sparks there on the brushes. Not too much, but some is normal. Seen that on like old drills especially. Here are those brushes. You can see them riding on the commutator. And that's a failure point big time. Some of the other things that make this a little bit especially relevant is if you have a brush, and let's say when the brush is kind of new, it's kind of thick, right? And when it's thick, there's a spring pushing the brush into the commutator. The spring's got a lot of tension, but as your brush wears and wears and wears, that spring starts to get overextended. It doesn't put all that much pressure on the brush. Does that make sense so far? Well, when the brush is kind of worn and the spring's not pushed on it, those brushes can get a little stuck sometimes. So if those brushes are stuck and you go to start the car and it doesn't start, how might you be able to unstick those brushes? What do you think? These brushes, bang, 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 bang. Hold the starter to the start position. Bang, 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 boom, and it worked. And you're like, aha, I fixed it. No, you just temporarily unstuck the brushes. So guess what's going to happen next time? Maybe it'll start, maybe it won't start, but eventually it won't start, right? So like, I'll make sure you understand this really well. My wife knows some stuff, but it's come through the school of hard knocks a little bit. So her dad had a 96 Jeep Cherokee, and one day they called and they're like, hey, the Jeep won't start, it's in the driveway. So I go over real quick, down and dirty, and if I were to go ahead and I were to look at this diagram way back here, I'll tell you exactly how I diagnosed it. Way back, this one, in fact, it's an auto, so I'll go here. I check here, it's got 12 volts. I check the case, it's got ground. Generally, I don't even do that. I put the wire right here and I tell her, I put my meter right here for available volts and I tell her, hey, turn the key. It gets me 12.6. And yet the starter just goes click, click, click. But it's got 12 volts and ground. What's wrong?
Motor.
The starter itself, whatever. I don't really care if it's it actually probably is the motor because I remember the solenoid clicking, but whatever, it needs a starter. So I said, yeah, you need a starter. I'll get it tomorrow. Okay, I'll be back tomorrow with it. I'll get it for you. Cool? So what do you think she does? She's like, and remember, we're from like a small town, okay? So don't judge me on the Walmart comment, but in the small town, there's really only so many places you can go. So she's like, and it's cold and it's winter and it's snowing outside. And when you can't do something, you're like, I need to go to Walmart. I don't really need anything, but I'm gonna go to Walmart because I need something. So she goes to Walmart anyway. She knew, don't drive the car. The starter's no good. But guess what she did? She went out and she tried to start it and it started up. And so she's like, oh, I guess it fixed itself. And she goes to Walmart and then she parks and she goes around the store and she gets nothing that she didn't need in the first place, but she got some steps and stuff. Then she goes out to the parking lot. What do you think happens?
It doesn't work.
No start. So then she calls and I think I was at work or something, so this story is a little fuzzy in my mind. It might have been the next day. Maybe I couldn't fix it till the weekend, but I specifically remember her calling and saying, hey, the Jeep won't start. And I said, yeah, it needs a starter, remember? So don't drive that one. She said, well, I already did, and I'm at Walmart, and it's cold, and I tell her, like, okay, you're gonna have to go under there and roll around in the snowbank, and you're gonna look for a starter. And she said, okay, I can do it. What's it look like? Like, how would you describe this? Now, at the time, she's probably like, yeah, she's probably like 18, so I'm probably about 18, maybe 19, and I'm like, it kind of looks like a soda can with a little thing kind of next to it, and she's like, I don't see that. It's dark, and she can't really tell, and some sweet lady comes by, and she sees her feet sticking out in the snowbank. She says, hey, what are you doing under there? And she's like, I'm looking for the starter. And the lady's like, oh, I know what that is. Mine was bad too. And they're both under there. So there's 4 sets of feet under there. And they finally bang on the right thing and then it does start. Okay, so that's one way to diagnose this if you don't have any tools is if you bang on the motor and it works, there's a good chance these brushes are starting to stick. There's a good chance those brushes are kind of worn, right? So she did get it going. She learned the lesson. Now she knows. Now she's kind of gone the other way. Like if she thinks, is there any chance this is going to break down? No chance at all. How do I know? How do I know the status of these brushes? I can't really tell you if the car is going to break down or not. One day these brushes are good and free, and the next day they stick for the first time ever, But it was a fun experience at the time. So you can see the brushes from another angle here with the commutator removed. So this is all failure point stuff. If you wanted to rebuild a starter, it's mandatory that you'd redo these brushes because that's like the #1 failure point. Even if you buy like a saw from Harbor Freight, a lot of times they throw brushes in the bag just so you could fix it once because they know they're going to fail. Pretty common. The other thing that could happen is if it does have the permanent magnets and then it also has those the armature has those fields in there, there's always a chance that this armature, like see this segment right there? What if one of these segments in this motor were to fail and it happened to land on that one? It might have a little bit of tough time starting, and sometimes banging on it can move this just a bit and help get it going, right? So we have seen that as well. And that's one of the reasons if you start to have some different segments in this armature fail, that starter will lose a lot of its torque. It might still work because it might skip over it though.
Like this Malara.
I don't remember what's up with that one. Will it start?
If you bang on it sometimes. But
oh, okay. Tough to tell if it's
bang on the starter with a screwdriver and a hammer.
Tough to tell if it's one of these segments or if it could be the brushes. Either way, it needs a starter.
Paul, when you say bang on the starter, where do you bang it on?
All right. Let me get my fake hammer. So if I were to do it really gently with this screwdriver, generally the place to hit it, if it's one of these, is right in here.
Oh, in the middle.
Yeah, right on the motor itself. And you just kind of do, and you could probably hit it over here too.
Yeah, because I reckon the
This would probably make more sense.
Yeah.
But sometimes, you know, it's like there might be a cable here, and usually the starter's like this, so it's kind of hard to get the hammer up here like this. You might be able to just do this.
Okay.
I think it would actually make more sense to hit here.
Right.
Also, if you buy a remanufactured starter, sometimes it will say do not bang on the case, because you bang on the case and now it's messed up and they can't rebuild it. However, in Walmart parking lot, I promise you that starter's getting hammered on.
Pro Jeep owner move. Hit the starter until it starts.
And it probably will, at least a couple more times. Fuel pumps, power windows, all the motors, any motor that works that way, sometimes free it up a little bit, help it out. Okay, then remember how we showed that magnetic field and stuff? Now this just shows you a little bit more of a complete view. So remember how we had just the two windings, right? There was the positive and the negative, and now you're looking at like, oh, the positive's right here, that's gonna magnetize this one, and that's gonna push downward movement. And then if we were to flip it around the other way, because it's on the next segment, it's gonna have current flowing the opposite direction, which is gonna change and move the direction based on the thing that you told me, right? So if you look at this, everything you learned about the single winding was true, except look, you've got like a lot of them, 8, 12, 16 maybe. You're gonna have a whole bunch of different segments, and this is just gonna switch back and forth. Positive, negative, and then negative, positive, positive, negative, negative, positive, all based on that. So you're just gonna have a whole bunch of those, and the reason I find it to be helpful is if you were to have one of these segments in the armature go bad, that's one of the reasons it could be sticking to. And exactly in detail, you know, I don't exactly know all the theories and all that stuff because we're repairing them, not really designing them. And so what this is saying is details about how the starter makes its power. So like, for example, current carrying conductor at a perfect right angle is going to have the most torque, etc. Conductor loop that can freely rotate within the magnetic field is the most efficient. Motor causes a loop to rotate until it's at 90 degrees the magnetic field. And then to continue the rotation, the direction of current flow in the conductor must be reversed, right? So it's saying if you're coming up to this point, it's like gaining the most torque right here, but then once it hits 90, let's say it's to here, once one of these segments hits 90, it has to reverse it. And that's why we end up doing the commutator to reverse the polarity, right? So that's what it's saying in so many words, to maintain the rotation. Cool. So this one shows it with 2. This one shows it activated a little bit more. Makes sense. And then in reality, you know, we're not going to have 2 segments. We're going to have a bunch of them. Cool. So that's pretty standard. And then they can even get into like the different designs that they have. So if this had 4, you know, you could see you'd have multiple loops. Cool. And overall, this just really evaluates the solenoid just a bit more. So if you were looking at this again, and this is a gear reduction type, which is the first time you've seen the cutaway, you see the motor right here, that's the motor. See the solenoid right here, there's the solenoid. Then you see the gear right here, there's the gear, and that has the one-way clutch on it. So on this gear reduction type, if we were to look at it, battery brings in 12 volts to here. Makes sense? But this 12 volts won't necessarily contact down here and run the actual motor until we activate the solenoid. And so the solenoid is going to be controlled through the start switch. So if we have power here and we send it to the start switch, it's inactive until we pass power through the start switch, the neutral safety switch, the clutch start switch, whatever, and then it's going to activate the solenoid. And when it does, you can see it's actually going to pull it over and it's going to contact right here. And when it contacts right here, the big battery power will actually jump over to this wire and run the actual starter. Right? So just kind of confirming the solenoid function. Okay, makes sense? And then when we talk about these two, you guys can recognize this big one up here. That's like the big positive. See this little wire? Sometimes they'll call it the S terminal. So if you were looking at this one, you could call this the S terminal, this little spade, that's the small wire. Makes sense? If it was this one, this is the big positive, this is the S terminal. So there's always going to be the small wire there that's really controlling. That's the start terminal, if you will. So on that previous page, Priscilla asked, what the heck is ST? It's just start. So some manufacturers will say S terminal, some will say ST, some will give it a number, but all the starters are going to work really similar. Makes sense? I think we're probably, solid on that solenoid. Good enough. Now, let's say you want to test it. Okay, I'm going to walk you through. First, test the battery voltage. You know that you can't test your starting system unless your battery's good enough, right? So if you have a totally dead battery, let's say your battery voltage is 1.2, you think that's enough to do the solenoid or anything?
No.
No, done. So test the battery first. At least the battery voltage. If the battery's fairly charged, then go ahead. What I would do next, test the S terminal input on the starter solenoid if the battery's fully charged and the starter doesn't crank the engine. How do you do that? How would you test the S terminal? Remember, this S terminal is the small one, right there. When would the S terminal be powered? Yeah, so you kind of need two people right now. You say, hey Tony, how you doing? Can you come over and hold this to the start position? And then real quick and dirty, you're just going to go right down there to the S terminal. And you can
That's
do
the little wire.
the little wire, exactly. You could test the big wire too, but like the big wire, I don't know how you wouldn't have 12 volts down there on the big wire because that wire is huge, so what the heck happened to it? If it's chewed, you're going to know. If it's cut, you're going to know. Make sense? Yeah, go ahead, test the S terminal. And if the S terminal doesn't do, if it's got 12 volts on the S terminal and the starter doesn't engage, your diagnosis is done. You could do that right in the driveway and then tell them don't drive the car to Walmart no matter what, and they'll do it anyway. Okay, makes sense? You want to use a test light? You can. You could even use a different type of light or whatever. For me personally, though, I'm probably going to use a meter. And part of the reason why, if I use my meter and I set it to record or min-max, I could actually do this myself. So I'd hook my meter up. I'd hook this up for available voltage on the small terminal. I'd put my meter on min-max. What's it read when I'm not turning the key?
0.
Zip. What should it read when I go in and turn the key? But I wasn't there to read it, so if I put the meter on min-max, I can come out and be like, did it ever get 12.6? Oh yeah, the meter says it did. Okay, cool. So I'm getting my signal to the S terminal. If the S terminal gets the power and the solenoid doesn't activate, your solenoid's no good. It's that simple. Makes sense? Keep it really basic, and that's kind of why they're saying the min-max is really nice. Now let's just say, that's the ideal, right? And that's what I got in the driveway when I told her, hey, this Jeep needs a starter, don't drive it. But let's just say I get down there and I don't get 12 volts. Then what do I need to do? Practical application. You know it's not the starter, right? Well, what is it?
The fuse.
Maybe the fuse. Probably not, because the battery was charged. Oh, I got to look at the diagram. You're right. You got that. So at that point, we need to look at the wiring diagram, determine how the circuits run, what other parts are in there, and then we're going to have to actually do the step-by-step. We're into wiring diagrams at that point. Make sense? And then, so we would proceed with that, but let's just say you were to start it, and then the starter were to not disengage itself. What do you think could cause that? Like this. Starter doesn't stop spinning. It could be, if it's getting 12 volts on that S terminal for whatever reason, that would be it. Maybe the relay's sticking, maybe the ignition switch is sticking, maybe somebody sent 12 volts to that wire in a jumper somehow accidentally. Or it could also be a spring that's failing to retract. So when we throw the solenoid, we give the power to throw the solenoid, through magnetism, but what returns it's actually a spring. So if I were to pull this out, a spring actually pulls it back in. Makes sense. So we could potentially have a mechanical failure on the spring. It's also possible that, like it's saying, these relay terminals could be welded closed. Even inside of the solenoid, that could weld closed. So this is not really common, but it does happen sometimes, especially on those contacts. And then just remember, on that starter circuit, we have safety measures to make sure it doesn't start unintentionally. So here's a more complete diagram. So if we were to trace this, here's your battery. Mason said it could be the fuse. Could be. There's the fuse in the circuit. Is this the only fuse? No, there's a big fuse right here. But if it comes off the battery and it goes up here to the alternator and then it goes through some other fuses, and some of these fuses are going to go to the ignition switch, but it also pulled off down here and it went straight to the starter. This one right here a lot of times is not fused. This cable is too big and it's going to pull too many amps to fuse that, so they typically don't. That's the big cable that goes to the starter. Cool? But then the control side is going to go up through a couple circuits. Now in this ignition switch is kind of interesting. This ignition switch is like two ignition switches in one, if you guys can see that. One of the ignition switches goes to the park neutral. One of the ignition switches goes to mostly to the ignition coils. So remember how when I said when you turn the ignition on, you're turning on the ignition system? That means your spark plugs are going to be ready to spark. The ignition switch has to do that, but the ignition switch also in the start position has to go down. So if we trace that, it's actually not so much going to be this one that we're real worried about. We're more worried about this one up here. It's going to go down through this connector into the park neutral position switch, through the park neutral position switch, to the coil side of the relay, right? So all this in pink in the start position, that should have 12 volts. Then after the coil side of the relay, it should be ground. And can you tell it goes right through here, through this part, which is a junction box, and then it goes all the way to ground itself. So this one's grounded all the time. We're controlling this relay on the positive side. So you might say it's source controlled or power controlled relay. We either give it power through the ignition switch and through the park neutral, the neutral safety switch, or we don't. So let's just say you're in park, but you don't turn the switch. Would we get voltage down here? Oh, bummer, you really can't see the colors. I can see the colors really rich on the other screen. All this kind of like gray looking thing is a little bit more pink. So if you don't turn the ignition switch, do we ever get 12 volts down here? Right. When you turn the ignition switch, it's got 12 volts. And this switch, when you turn it to start, should pass it through, pass it down, get 12 volts here. If you don't turn the switch, it's not going to start. You all know that, right? But what if you don't have it in park or neutral? It's also not going to start. Now, typically, it's not operator error. So I want you to think about it like this. What if the contacts in this switch were no good? You turn it, but it never passes voltage through because the contacts are bad. Couldn't this problem be an ignition switch? How would you test it? It could be the fuse. If you thought it was the fuse, you could do 12 volts here and 12 volts here, 12 volts here and 12 volts here. If you had 12 volts here and 0 volts here, yeah, the fuse is blown. Why is it blown? Well, we'll find out. But let's just say it's not the fuse. Let's say you have 12 volts here and 0 volts here when you're in the start position. What's wrong? Bad ignition switch, exactly. You guys remember how we diagnosed those on the board? Who cares if it's an ignition switch, a window switch, a lock switch, a made-up switch, a fog light switch, whatever you want. We test them the same. If we have 12 volts going into the switch and 0 volts coming out, that switch isn't giving good continuity. It's got excessive resistance in the switch that's going to cause a voltage drop, right? So let's say we diagnose that and we're like, okay, yeah, it's 12 in, 0 out, so it's a bad switch. We put a switch in, now it's 12 in and 12 out, but then it still doesn't start. Let's say we go to the park neutral switch and we've got 12 volts at the park neutral and 0 volts coming out. Apparently it's the switch. We might just have to make sure that it's an adjustment, that it's actually in park. You ever seen the old cars where you put it in park and the reading's a little off and you got to wiggle it a little bit, you know? So there's an adjustment here that might be a problem, but if the adjustment's good and it's 12 volts in and 0 volts out, this switch is no good too. It doesn't matter it's possible it could be more than one thing. Why it would be, I don't know. But right, so we're just going to diagnose it just like we would diagnose as if this was a light bulb. If this coil was a light bulb, you guys would know you have to have these switches on for that light bulb to work, right? So don't be scared. whether it's a light bulb or a coil of a relay, it's the same diagnosis procedure. That we spent weeks on that. So you should be pretty good. Right, and then if we were to, let's say, repair the switch and then it gets 12 volts coming out, but let's say it has 12 volts here, but it doesn't have 12 volts here, what are your thoughts? If it has 12 volts here, let's say I'll just start tracing right here. It has 12 volts here, 12 volts makes it through, but then somewhere right over here, I do a check, and I'm getting 0 volts right here. Then what are your thoughts?
That's huge.
Well, we got 12 volts right here. How could it go from 12 to 0? What is all this stuff?
Wire.
This is just a wire, and this is a connector. It's not really a fuse, but if it was a fuse, I'd suspect it. But yeah, then you'd be like, hey, you got a wire, and sure enough, you dig in there, you know the wire that goes to the little terminal, the S terminal? You're like, oh, the mouse chewed it right there. And now you go ahead and you fix it, right? You fix it, and now all of a sudden you know that it goes right to here. And let's just say, I'll really go with this one. Let's just say that it still doesn't start, and you don't hear the start relay click. What do you think it could be?
The relay.
It could be the relay. What does the relay need to magnetize? It's got the 12 volts. What's it need down here? And let's just say this ground is messed up. So you're like, oh, there's no ground right here. Then you find this ground down here is messed up, and you fix the ground. And now it gets 12 volts and ground, and it still doesn't click. Then it would be the relay. Then you're like, oh, it needs a relay. So you put a relay in, and now the relay clicks. You can hear it. It goes click. Cool. But it still doesn't start. And then you're like, man, I hate this car. No, we're almost there. Just follow it through. You know that if that relay clicks, that just means it pulls this switch into contact, right? Is there 12 volts here or not? I don't know. We got to check it, right? So you could drag your meter over here, and let's just say there is 0 volts. Should there be 0 volts right there? Trace the circuit. We should have it like this, right? We have the ignition switch. The ignition switch is new now, so let's just say it's not the switch. The switch, it should come out here. It should go here. Let's say we had 12 volts here, but 0 volts here. What's wrong? Yeah, that wire, exactly. So we're like, that mouse chewed another wire. Then we fix this wire, and now 12 volts down to here. But let's just say we have no 12 volts right here. What you call it? This is kind of a switch, right? But this switch is part of what's this thing?
Relay.
The relay, yes. We're like, oh, it's got bad contacts in the relay. And then we end up replacing the relay. Cool, so if you have 12 here and 0 here, this relay is either A, not commanding, it's not being magnetized, but we check that, right? You can hear it click, so you know it's being magnetized. It just might have dirty contacts right there. So you replace the relay, and now you got 12. And then the 12 makes it, let's just say, down here. And it goes and stops right there. Let's say we have 12 here. And let's just say we have 0 here. What's wrong there? Is it not quite to the starter yet? It's 12 coming out of this jump. Exactly, another wire's chewed. So we fix that wire, and now we have 12 volts. And let's just say we verify the 12 volts here. We verify the 12 volts here. It's got both, but it doesn't start. What's wrong? Yeah, exactly. Now it's a start, right? So you just came through all the possibilities realistically, right? If this starter has 12 volts on the big wire and it has 12 volts on the little S terminal and it doesn't work, the starter's no good. What's no good? I don't know. Probably the solenoid, or the solenoid has a little circuit inside and some different things. But if you can verify the starter has 12 volts and it doesn't work, the starter's no good. Assuming it has a good case ground, which I don't even know how that could actually fail. It'd have to be maybe somebody painted the engine block and they just bolted the starter up without cleaning any paint off of the surface. I don't know. Probably not going to happen. Cool. So if you were to look at this real down and dirty simple, remember how I diagnosed the Jeep in the driveway, right? I went straight to the S terminal. And I said, hey, can you crank it? She cranked it, it had 12 volts. You know what that tells me? All this stuff is good. I'm not gonna test the relay, I'm not gonna test the fuse, I'm not gonna test the connector, the neutral state, none of that stuff. If 12 volts made it to here, all this crap is good. And this is good, and the switch is good, and the fuse, everything is good, except for the starter. So see, in one test, you could totally knock that diagnosis out. Okay, make sense, kinda, sort of? All right, good. Or, if you don't have any tools, except for maybe the meat hammer, you could punch the starter, and if it starts, you're probably like, oh, it's got a bad starter. With no tools. It might hurt though. I'd probably use the meter. I'd recommend the meter. So, or at least like the handle of the hammer, if not the metal part of the hammer. Cool. Now let's just say this is slightly different. This isn't a no crank, no start. This is, it cranks, but it's kind of like, ruh, ruh, ruh. What are your initial thoughts? It could be the bad battery, right? So we learned how to do a battery test. If we do the battery test and the battery has high cold cranking amps, it's not the battery. However, look, the battery's got a terminal, and that terminal goes to the starter. How do we know this terminal's good? How do we know this terminal's good, right? We can voltage drop test that. The alternator we cover next week, the alternator's job is to charge the battery. When we're going to start it, the alternator is not relevant at that point yet. Now, if the battery dies while driving, we're all over that alternator. But if we're just trying to start it and it's cranking slow, it could be the battery, and it could be the battery because the alternator, but if we test the battery and the battery tests good, we're more looking into is it a voltage drop on the cable? You know, is this got a big voltage drop? Does this have a voltage drop? These types of things. And if we check the voltage drop and this voltage drop is less than a half a volt and it still cranks slow, we might look into something different. Maybe the engine's starting to seize. Make sense? But at a minimum, we check this, and if this is good, it's good. Now, if we check this cable and it's dropping 2 volts, then we're like, hey, it's got a bad cable. Let's replace the cable. Make sense? So you got to prove what's bad and not just guess. Make sense? So that's overall probably pretty good. Now just let me introduce you to this cranking hold feature. Have you guys ever jumped in a car and you turn the key and then you don't have to hold it anymore and it continues to crank until it runs and then stops cranking on its own? That's kind of nice. They'll call that sometimes cranking hold. Now when we do that, we integrate a control module. So it's generally the engine control module or the powertrain control module. You're basically, if you were to summarize this whole diagram, without going all crazy, it's almost the same, except you go to start it, and what you're really doing is sending a signal right here. You're saying start switch signal. The ECM gets the start switch signal, and then it's like, okay, I take over now. Now the ECM is going to use the STA to send some signals, and it's going to use the start control to basically provide, if you trace it all out here, that's going to provide the 12 volts to the relay. So in this system, what's actually controlling the 12 volts to the starter relay? Is it the key? Is it your ignition switch? I just explained, your ignition switch gives a signal to the ECM. The ECM is actually the one controlling the starter relay. Why is that better? Or is it better? You can't hold it cranking too long, but also you jump in the car, you hit the key, you don't have to really hold it and listen, you just hit the key and the ECM will crank it until it sees crankshaft position sensor speed.
So when people half crank it stops it from half cranking too?
Exactly. So you ever jump in the car and you like kind of crank it, but you don't hold it long enough?
Yeah.
Not with this system. This system's like, because that sounds like there's something wrong with the car. Yeah. This is going to make the car seem a lot more nice, high-end. It's like, it fires up every time. If you talk with some people, they're like, that car fires up every time, right away. Well, this gives the perception of, I barely hit the key and that thing was running. Yeah, The computer held it longer than you did. But sure, if you feel good about it, great. So this is a feature where the computer controls it. This was how it started, but you know these cars that start, stop, you come to the stoplight and it shuts off and then it restarts? Did you push the key?
No.
No, the computer did. The computer controls the relay. Well, and they hate you too. No, I get you. It's kind of a hassle.
Once you're at a stoplight and it's green, you just have to wait a little bit, then go.
It depends on how well they make them. So some of them will hold transmission line pressure, hold everything, and like the second you push the gas, you're moving. Some of them are not that good though. I'll give you that. It's also kind of weird because it's like if you're trying to blast AC, it'll shut off and the AC will be cool for a bit, but then the AC will start to blow warm and then it'll start back up and then it'll shut back off. So I get you. But you know why it's on there?
Asshole.
Two reasons. One, fuel economy. You like better fuel economy or you like worse fuel economy?
I just want the gas to be lower.
That would be good. The other thing is lower emissions. So when they look at fuel consumption and lower emissions, they realize there's like a substantial fuel consumption and emissions produced by idling vehicles. So they come up with, this system. And remember, the manufacturers are being squeezed to try to hit these big corporate average fuel economy numbers and try to get their emissions very low. So this isn't a system that they thought, hey, this is what the customer wants, as much as this is what they need to do to hit their standards.
So when you're working on a car that does that,
Sure.
what happens when is everything still on? It's just
That, we would have to get into a whole bunch of detail, but what I could tell you is all this stuff is powered up. Your computer controls the relay, but your computer also controls things to help it be ready to go. So like, a transmission has to build up pressure, right? Yeah. And the pressure comes from the engine running, but if the engine's off, the transmission loses pressure. They put an auxiliary pump to keep your transmission pressure up. So sometimes on the start-stop, you hear some weird noises, and that's it running several smaller systems to keep it ready to go, and then it goes. So saving gas, lower fuel economy, I agree, but this system becomes more complex. So rather than going straight to the starter, now we're looping the ECM in. What happens if the ECM has a circuit failure? It could be a no start. So remember how we were saying a no crank, no start could be the ignition switch and the relay and the fuse. Oh, I just added a $1,000 computer that can cause your no crank, no start because the computer controls the relay. Make sense? More complex, more difficult to diagnose. Additionally, when we add these other systems, like this starter is beefed up. This is going to be a stronger starter, better contacts, longer lasting brushes. This starter is going to be substantially more expensive because it's made to start it at every stoplight too. And additionally, sometimes they have counters, like we were saying. If you hit 100,000 stops, it's probably going to give you a service message saying, hey, you need to replace that starter because we know it's done. It counts the number of stops. When there was no computer involved, they couldn't count. Now that the computer's involved, it's counting the number of start-stops, Once it hits a number, warning message is on. Warning message won't go off until someone goes in and replaces the starter and then tells the ECM to clear that message. And then it'll be off. Makes sense? So you pay for it one way or you pay for it the other way. You save gas for these years, and then you go in and replace a starter that wouldn't have failed, except it was overused.
And I think those are the ones that just turn off too with a button, right?
You can. So you can do the start, stop, cancel, but it's actually federal law that if you want to cancel the start, stop, it has to turn itself back on the next ignition. So you can't just cancel it and forget about it. You have to cancel it today, and then when you shut it off and turn it back on, cancel it again tomorrow and cancel it the next day. I don't know that I'd bother really canceling it, but I'm just saying that's the broad picture on how this works. It all started with making the ECM control the relay. You couldn't do it before the ECM was a part of it. So you'll notice more and more computer control pretty much on all these systems. And then here's what it kind of looks at in the programming aspect. They look at the timing chart. So they'll say like, if it's a crank hold, how long will we crank it? They'll let it crank between 2 and 25 seconds. After 25 seconds, it won't crank anymore because beyond that point, it starts to damage the starter. You ever heard a car that doesn't start and the people will crank and crank and crank and crank and crank for minutes? That will kill your starter, just letting you know. You need to stop, let the starter cool down. So there is a positive of this. It's to prevent people from leaving the starter engaged too long, and also from cranking it too long, right? So when they hold it after the engine starts, that damages starters. But also if the engine doesn't start because it's out of gas or whatever, it's to prevent them from damaging the starter from holding it for more than 25 seconds too. Both are there. Okay. Then we want to get into diagnosis and testing. This was a really good shot of a front wheel drive 4-cylinder. You know, the starter's right there. It's not that hard to get to. The testing is nice, really good. Hitting it with the hammer is pretty nice. You're not in the snowbank with help, right? Right there is pretty cool. They're not always that easy though. You wait till I show you a slide at the end, which is my picture. So both. Easy enough to test, easy enough to get to. Some of them are really a hassle. This one's about as easy as they come. So in our diagnosis and testing, visual inspection, current draw test, voltage drop test, operational continuity checks, and then even starter motor bench testing. And we'll hammer right through these. So visual, look at the battery. If the car doesn't start and you pop the hood and the battery looks messed up, you know, you might be like, hey, that battery is suspect to me. Like, let me check that battery out. Make sense? You could check the state of charge. Sometimes they have a little eye on them and you can look at the color, but those are pretty much gone. If you want to check the state of charge, you need a meter, so it's not so much visual at that point. But additionally, you can look at the starter, damage, corrosion, loose mounting hardware. If you see something that looks like someone just worked on, that's kind of a clue, right? And inside in the ignition switch, look at the switch. Is it a key that looks like it was just cut, that might not have, you know, the security chip that it needs? Does it look like this has been tampered with? Did someone try to break into the car and try to force this to turn with a screwdriver? Like, you could see that, right? Don't overlook those visual things.
Or USB thing for Kias.
Oh, no, you don't. Yeah, so if somebody's been in there doing that, right, they could damage it. Make sure it moves smoothly. And then we'll actually get more into not so much of the visual, but into the actual voltage drops and these types of things. And also just check, see if the key looks like it's got excessive wear. Sometimes that happens. Now let's discuss, I don't think I just skipped. Yeah, we're good. This is gonna tell you a lot about the system. So we're gonna go over it and then we're gonna touch back on a little bit more. If you wanna know how much current the starter draws, that can tell you a lot. I'll tell you what it tells you in just a bit. This is how you do it. We're going to check voltage with our meter, and then we're going to use probably another meter, and we can actually do an inductive amp clamp. So remember how our meter can only handle like 10 amps, right? This sucker could be 200 something. So you can't open the circuit and put your meter in series. You're going to explode the meter. That fuse would be like gone. It could do a lot of damage. So if that's the case, we use an inductive amp clamp. You know, we talked about this in the beginning. This amp clamp doesn't touch it. It goes around it and it measures the amount of electrons, and then it'll give you how many amps. Make sense? That's how we're actually going to test it. Now, where are we testing it? During cranking, we generally just do it right at the battery ground. You could even do it at the battery positive if you want, because essentially all the electrons leaving the battery, they're all going to the starter. Yeah, they might be running a couple other things, but like this is going to give you a pretty close number. If you want it to be exact, you'd actually have to go to the starter like this, and you'd have to get this wire and amp clamp this wire. Make sense? But sometimes that's pretty hard to do, and so in this case, we can get a pretty rough number here. It'll be pretty close. Then we're going to measure how many amps, and this is showing millivolts because this has to run a calculation to make this amp clamp work. But in reality, we want to measure the actual amps. Okay, make sense? And then if we want to do voltage drop, it's a little different. Let's just say you wanted to measure the voltage drop of this battery terminal. You'd put maybe your positive lead right on the positive terminal of the post of the battery, and then your negative lead is going to go on the clamp of the actual battery terminal, right? So one would be on the post, then the other one would be on the clamp. How many volts should it drop, would you say? Like basically nothing. It shouldn't really drop more than like a 0.2. Definitely not more than a 0.5, but like even a 0.2 would be probably pretty much the limit. Okay, and then if you look, well, next time don't shut it all the way. Then if you look, we're going to do, how about we could do the terminal, but let's say we want to test this positive cable. This gets a little tricky. We got to put our our red lead on the positive terminal, and then our black lead is actually going to go down to the starter on the big wire. Does that make sense? What are we actually voltage drop testing in that? We know it's this wire, but what is that wire?
Cable.
That's the whole big positive cable. Now, they give you up to 0.5. You want to know why? Because you're going to test this while it's cranking. You're not just going to test it with it off. It's going to pass while it's off. If you know how we test things like under load dynamically? Remember how we test people? We put them up on the treadmill, run them as hard as they can, stress test them and see if their heart's any good or not. Same thing. If you want to really test this cable, it's got to be during cranking. So you do positive on the positive terminal, negative on the other end of the cable of the cable at the starter, and then you're going to actually crank it and see how many volts drop across the wire, across the big battery cable. That make sense? If it's more than 0.5 volts, it's no good. We give it a little bit more leeway there because it's such a high current cable. Cool. And then we could voltage drop all this other stuff too, but generally for the starter, if it's like a slow crank, we're worried about the terminal, we're worried about the big cable. Kind of make sense? That would be a battery cable voltage drop test. And so that's kind of what it's showing, right? So, and if it's on the ground, by the way, we can voltage drop the ground too. How does this starter get its ground? The case, right? The housing goes to there. So we would put one lead on the housing, probably the positive, and then the other one we put at the negative battery terminal, and we can see how much voltage drop it's dropping through the chassis ground. And we want 0.2 or less. So that one we don't give quite as much leeway because it's got the whole chassis ground. Whereas the positive cable has just got the one cable, so we give it a little bit more leeway on the test. Make sense? And then same with the negative battery terminal. So if you do those couple checks right there, that tells you if your battery cables are good, if your battery terminals are good to the starter. Makes sense? That's a good summary of the battery voltage, of the starter voltage drop. All right, and then when we look at this, this is more showing you what the voltage drop across the solenoid is. So this one's slightly different. If we were to look at this terminal, big battery comes in, right? When the solenoid throws, remember how it makes a little electrical connection? We shouldn't drop a lot before it comes out here to run the motor. So you do here to here, and then crank it and see how many volts it drops. Make sense? That's testing the actual internal contact of the solenoid, and we could get potentially up to 0.3, right? So overall, we should be under 0.5 on everything, though, if you just keep that one in mind. Kind of makes sense? You guys understand that's testing the actual solenoid contact. Cool. And then now, if we get into starter control, that's different, right? Everything we talked to in the previous 5 minutes is going to be like a slow crank, or it doesn't quite have enough power to start it, but I can hear it cranking, right? That's all true. This issue up here, this is more going to be like a no crank, right? If this relay doesn't give a signal to that little S terminal, it's not going to make it crank slow. You guys understand that, right? No power to the S terminal doesn't make it crank slow. It makes it not crank at all. Cool? So if it's like you turn the key and it just goes like click or not much sound, the next step we're going to do is, yeah, go ahead. The next step we're going to do is we need to determine if we could do it a couple different ways. We could do voltage drop, but let's say you want to voltage drop the switch. How much should the switch drop? 0.1. Let's say you wanted to voltage drop the neutral safety switch. 0.1. Let's say you wanted to drop the clutch pedal switch. 0.1, right? On the control side, we should really have little to no voltage drop. But you got to determine, are we pursuing the control side or like the big power side? If the starter's not starting at all, we're after the S terminal, the small terminal side. Make sense? Checking all these types of things. So this likes to do voltage drop. The other thing you could do is put your negative terminal here, 12.6 here, 12.6, 12.6, maybe 12.5, 12.5, maybe 12.4, right? You could do available voltage too. But if you want to do components, boom, it should be 0.1 or less, boom, it should be 0.1 or less. Okay? Now, how do you want to test the starter relay? This gets tricky. You guys remember way back, who got to successfully test the relay? That was kind of hard to do though, huh? Because when you want to test the relay, you got to think about it. Right here, terminal 1 and 2, can you see what this one does? That does the magnetization. You can check resistance of this coil, but how could you actually check to see if this contact is clean between 3 and 5? That gets tricky. You could do a voltage drop test or you could do a resistance test, but the problem is you have to actually have this be activated. How would you activate the magnetic part of the relay? Remember the jumper? Yeah, so we jump red to here, we jump black to here, then we can measure 3 to 5 for resistance, or we could measure voltage into 3 and voltage out at 5, and it should be, under 0.2 or so voltage drop, right? So that's how we'd actually test it. You can see right here, we are using a battery on this terminal and a ground on this terminal, so a battery to 1 and 2, and then testing resistance from 3 to 5. Cool. Another thing, and let's just say that you're in a jam, you can probably switch relays, but sometimes your starter relay is made for more current and it's special. So you might not be able to. And sometimes it's the same as other things, but if you switch your starter relay into some unknown spot and then you put you swap the other relay into starter and now it starts, it's the relay, right? But what happened to your old relay? Where'd you put it? I don't know, I lost track. Well, the customer's got something that's not going to work now. Hopefully it's not the fuel pump. Hopefully it's the fog lights. Hopefully it's not the horn and they have to beep and it doesn't work and then they sue you. See what I'm saying? So it's not best practice to do swapping. However, sometimes I do that too. Cool, now if we get into the neutral safety, remember how we could test the neutral safety electrically, right? But you also have to be worried about that adjustment we mentioned. This is just a sample. This neutral safety switch is on the transmission, and we need to be able to rotate it to have it indicate park or neutral before it'll start. So you got to verify it's in the correct position. That can vary from car to car. Big variations. Okay, now let me ask you guys, you want to take 10 minutes or you want to keep rolling it? Quick response. All right, Tim, will you pause me?
Okay.
All right, so you guys, for the part 2, we're going to pick up right where we left off. Remember how we talked about how to adjust that automatic transmission neutral safety switch? We also need to worry about our clutch switch. So if our clutch switch is out of adjustment, it may never actually make contact, right? So there is an adjustment here. It's not typically part of electrical. This would be probably more part of like manual transmissions that were down there working with clutch adjustments. But just know, because it could cause a no crank, no start, you have to be aware of it. Make sense? So there's a switch there. If you were going to try to test the switch, you could go ahead and put it on resistance. With the clutch pedal up, it should actually be OL. When the clutch pedal's down, it should have like a 0.1, 0.2. Makes sense? The switch should be closed when the clutch pedal's down. So you could do your electrical test right there. Another way to do it would just be to leave the switch right in there. And if you try to crank it, you'll probably have 12 volts on one terminal. And if your clutch pedal's down, you should have 12 volts leaving the switch on the other terminal. If you're losing your 12 volts right there, either it's out of adjustment or the switch is no good. Either one are possible. A little hard to say, right? So when we get into the starter a bit more, the main thing is getting to that small wire. So this one, for example, it's not C. It's actually going to be the S terminal. We're making sure voltage gets down there. And we could jump the starter. So that's kind of what this is showing. Like if you wanted to, you could actually jump 50. Actually, it's going to be the big battery cable to terminal C to check the starter. But if you do that, you only want to do that for like 5 seconds max because it gets really hot. Okay, so if you want to do some more bench testing, which, as a technician, this is not really what we do, but to illustrate it for you, if you wanted to do more starter motor bench testing, you could. We're going to replicate what we do in the car. you're going to go ahead and do an amp clamp on the positive. So that would be like right here. Then you're going to actually power it on. Like in this trainer, we could start it with the key. But if you were to jump it, like we showed on the last screen, you'd measure how many amps it pulls. That's going to tell you a lot about the starter itself. And we come back to the differences between like an electrical problem and a mechanical problem. There's a really good way to tell if it's electrical or mechanical. It has to do with the number of amps. Electrical is going to be too low and mechanical is going to be too high. Cool. But this again is no load though. This is not cranking the engine. So it tells us some things, but preferable to do this test in the car. Now why that's relevant, if you're doing bench tests, that's a little abnormal, but when you send your starter in, you know, like let's say you put a new starter in, you give them the core, the people remanufacturing it, they don't have access to the starter in the car. They can only do bench tests. So these are some of the tests they're going to do. Maybe someday we'll do these, but generally we don't. It's not as accurate as when tested in the car dynamically cranking the actual engine, right? So it talks a lot about this solenoid, checking the resistance of the solenoid from the small terminal, the S terminal to the case, etc. Same with, we could actually test the starter motor armature segments, right? So we're measuring from where the commutator contacts to the coil core should be like 10,000 ohms. So that's the spec. When you go from the commutator to the beginning of the segment, we should have below 1 ohm. So these are some of the tests that they do. And then also we'll go ahead and we'll measure the brush length. Length should be greater than 4 millimeters. As the brushes wear, guess what? 4 becomes 3, becomes 2. And if it's below 4, they need to be replaced, right? So this is a little bit more the guide for overhaul, but kind of good for you to be able to tell. What do you think's being tested right here? Yeah, exactly, the one-way clutch, right? So this is, you could actually do it without taking it apart. Ready? Spin, lock, spin, lock. So if you do have a starter, let's say you get pulled into something you didn't want to get involved in. Somebody says, hey, I replaced my starter and didn't fix it. Can you test my starter for me? And you're like, well, there's some things I can do, like something like this. We could do some of our minor bench tests, but best to do the diagnosis while it's in the car, while it's not working. That's going to be your better diagnosis. And then this isn't real common anymore, but it used to be, gets into shimming a starter. So back in the day, we had starters and they were always sitting a little bit different on the block, and the way they would engage the ring gear was a little bit different. So some starters will call for shims. So has anybody ever seen starter shims like this? That's how I know you'd be working on some older stuff. So newer things are a little tighter, higher standard, more precise. But older stuff was like, you might need to shim the starter out. You might need to remove a shim. There were some measurements. So if you hear stuff about shimming, this is why. If you have the starter gear in the incorrect position with the ring gear, the teeth will barely touch or they'll go too deep and they'll actually make noise in both cases. Like if they're just barely touching, they tend to scream and they also tend to wear the gears off. Then if they're too deep, they'll tend to bind and they'll also scream, and they tend to kind of bind up, and those starters tend to not free up. Like you'll release and it'll be stuck in there. Yeah, they get locked in, yeah. So this is old school shimming. Mainly first off, I don't really get involved in a lot of this because it's old school, but if I did, I try to avoid the measurements because it's a hassle. What I'll try to do is look at the teeth on the flywheel, and if you can tell the starter's gear's been buried up into the gear on the flywheel, I'd shim it more. And if it's just barely catching the edge, I'd remove a shim and we can get it to sit better. But luckily for you, it's not real common these days. Okay. Also, speaking of the starter drive, if you were to crank a starter, and let's say that it's the solenoid type, if this starter were to not kick out and engage the flywheel, it could just go zing, zing. You ever heard those? That's a lot of times an indication of a starter solenoid, like this one. Uses the solenoid to kick it out. Cool, so just being aware. Again, it's replacing a starter unless we're going to rebuild it. Remember, the ring gear as part of the flex plate or flywheel could cause some issues too. And then what's it say right here? No diagnosis of the starter drive should be concluded until the starter is removed and a visual inspection of the pinion drive, and the entire ring gear is performed. Remember what I was saying? You could have damaged teeth on the ring gear of the flex plate or flywheel. You got to really look that thing over. You know, you may tell the customer, hey, we diagnosed it as a starter, but once we do the starter, when we get it apart, we have to inspect your ring gear. If the ring gear is damaged, you may have to replace the flywheel or flex plate. That's a fair thing to say. You don't totally know what you got, but to say you need to take the starter out to determine if it's bad is sort of like you're already doing the job. So I'd sell the job and then say we also have to do an inspection, you know, while we're doing the job too. Cool. Now I'll talk about hybrids because you like these vehicles. Hybrids use both an ICE, you know what that is? Internal combustion engine, and electric motors. So a lot of times they're using high voltage. Sometimes they're using a high voltage electric motor for startup. Who's ever heard a Prius start? What do you hear? It's just like, vroom. You're like, where was the sha-na-na-na-na-na, right? So when we're talking about starters on hybrids, not all hybrids even have a starter at all. Cool, so boom, it's just running. Yeah, which is kind of cool, right? So I'll explain that to you. So the hybrids also can use auxiliary power, regenerative braking, all related to the high voltage battery, something we covered a little bit last week, right? But they have their own starting system too. On a lot of them, the main electric drive motor is used for engine cranking. So the same motor that is in typically the transaxle can start the engine or be driven by the engine. It can function as like a motor to start the engine, or it can be driven by the motor and function as a generator. So for that reason, a lot of times they'll call it like the MG, the motor generator. It's a motor, it's a generator, depends. Is it motoring the engine which starts it, or is it being generated off the engine which charges the battery, right? So just introductory to that. But on other ones, sometimes they do have a regular engine starter the first time, or if we have an issue where the high voltage battery pack is dead. So like, for example, we had a Wrangler, 2019, maybe 2020, Rubicon two-door with a 4-cylinder turbo hybrid. It was a cool vehicle. Yes, I had a Mopar, okay, but don't judge me. It was fine. But when you went to start it, it started conventional, and it was running. But then when you did start-stop, the starter never ran. It used something else with the hybrid system, and I'll show you. It was a belt alternator starter. When you come to a stop, it would shut off, but then when you get ready to go, boom, it was just running. The actual starter only started it at the beginning. Throughout your whole trip, the starter never ran again, which I think is a better system than the start-stop systems that use the heck out of that starter and kill it. All right, so and sometimes they'll use traditional 12-volt motor as the backup, like we were saying. But a lot of them, like most hybrids, because they already have that high voltage battery and they already have motor generator, we might as well use that, right? So if we were to say the advantage of the high voltage starter motor, such as the MG, right, the motor generator, MG1 we'll just call it, it's able to crank the engine at much higher speed than possible with a standard 12 volt. So now you've seen this little starter, and this thing can crank your engine, yes, but it might crank it a little too slow. And so if we have a big hybrid one, let's use that, it's nicer. Prius is a good example. You know how fast the starter can crank the Prius engine? 1,200 RPMs. So if you hear a Prius, let's say you run a Prius out of gas, totally dry, and it dies. If you go to start it, it's crazy. It doesn't sound like a starter. It's not like sha-na-na-na-na-na-na. It's more like this. It's like, and you're like, oh, it's running. And it'll do that for 30 seconds. It'll crank the engine for 30 seconds. Almost every technician I've ever met calls that a start stall. They'll be like, that Prius ran for 30 seconds and then it died. Because the MG can crank it so fast it sounds like a 1,200 RPM idle. And they're like, why is this start stall? It never started. It just cranked at 1,200 RPMs. The car's out of gas. They're trying to do advanced diagnosis of start stall and checking ignition and checking thing. The car was out of gas, okay?
They looked at the gauge
Yeah, but there's been a number of those. Sometimes, well, you know what you do? The KISS method. Keep it simple, stupid. If there's no gas, but it would throw a technician off because they're like, it's not a no crank. It's not a start stall. It's running and it's dying. It has nothing to do. Well, the starters and the hybrids can sound very different. That's really the point. Okay, and you can even see maybe even more than 1500. And then there are other types where the high voltage starter can crank the engine through an accessory belt by a motor mounted between the engine and transmission by the motor generators in the hybrid. So in like a Prius, there's a motor inside the transaxle that can start the engine. On a Silverado or a Tahoe hybrid, there's actually a motor in between the transmission and the engine that can start the engine or drive the transmission. That's like a bell housing motor. Or in that Jeep, there's a bigger motor generator that's basically like a super duper alternator with its own big fat belt, and that's hanging on the engine. All three of those could start the engine without a traditional starter. So you got to at least know a little bit about those because it's starting system. And that's why the starting system in this one's gotten so intense. Here's your hybrid transaxle version. Honda also uses a motor generator between, it's kind of in the bell housing. And then here's that belt alternator starter. It's a little bit hard to see in this picture, but it looks like a really big alternator, like 3 times the size. And it's got a big fat belt right here. That can start the engine. But how does that start the engine?
By the belt?
Yeah, it'll turn the belt, and the belt will turn the crankshaft. The next thing you know, boom, the engine's running, and it made no sha-na-na. You didn't hear the gears clash on the ring gear and pinion and stuff because there is none. There's just boom, and it's running. And this one can turn the flywheel directly, and this one can actually turn the engine through the transaxle planetary gear set and start it. So it's really interesting. They can all start it.
So the other one, the hybrid one, is connected to the time.
Hybrid, all hybrid.
That one connected to the time.
This one, you see these bolts right here?
Yeah.
This goes to the flex plate or the flywheel bolts. So sometimes they even eliminate the flywheel on these. They don't really need one. Sometimes they'll just put like a clutch or like some sort of a mounting plate.
What about the hybrid transmission?
And this one is a little bit complex, but you see, this is MG2 mainly to drive wheels. This is MG1. In the center right here, it's got, this is the stator. In the center, it has a rotor. And if the stator gets its 3-phase AC, it'll turn the rotor. And the rotor is actually splined to a planetary gear set. If anybody's taken automatic transmissions, you just are like, whoa, I remember those. So because that rotor is splined to the gear set, and a couple different members of the gear sets do different things, but one of the members of the gear set actually goes directly to the engine. So it's weird. It spins the transmission to start the engine. Basically, it's the short story of it. So just different. This one spins the flywheel directly. This one spins the transmission, which spins the flywheel, if it has one, which spins the engine. And that one spins the belt. They all sound totally different than a traditional starter. Cool? And this one uses high voltage AC to start it. So you know your little 12-volt battery? Has nothing to do with this. So if you have a Prius and you're trying to start it, you don't even need a big battery. It could be like a small. This is enough to run a Prius or any type of hybrid that uses this, because all this does is it basically wakes up the hybrid system, and then the hybrid big battery powers this, which starts the engine or whatever. Make sense? Similar with this one. This one's slightly different. This is typically like a 40, this will probably have like a 48 volt or a 36 volt battery pack somewhere. So it'll have your regular battery, but then it'll have another battery, but it might only be this big, right? When it's this system or this system, it's a big backseat battery. When it's this system, it might be like, you know, it's like the type of thing that you'd see like a power generator for your camping trips type of battery. It's not that big, but it's more than big enough to power this. But then once it's running, this can function as the starter and turn the engine, right? But once the engine's running, guess what this does? Runs as a generator, and the belt turns this, and now this charges that 48 volt battery pack. Can that make sense? So they're cool hybrid systems, but we're only looking at it from the perspective of starting for now. Cool, so now let's get into more starter testing. Remember we talked about the starter draw test? You see the amp clamp now going to the battery. This will tell us, it's a good indicator of Starter motor performance, we can do it on the car, off the car, on the car's preferred. And that's going to be a starter draw test. If it's off the car, we call it a no load test because it's not turning the engine. So if we were to do this, a lot of times what we'll do, we could use a big stand-alone machine. This is old school, but this has an amp clamp. We can go put it on there. Or we could use a more modern, like a fluke meter, and put it on there and measure the amount of amps. Then when you're going to crank it, this is going to tell you how many amps. Like right now, it's only 3.5. We're not cranking the engine right now. But if we were to disable the fuel and crank it, we'd want to get like a max reading. And let's just say it pulled 150 amps. That can tell us a lot about the system. So it's not a real complex test. See, we just looped it around the positive terminal. Might even be on the negative. I can't quite tell, actually. Okay. And so this kind of walks you through. This is using the old school machine. We're going to put this on here because when we do this test, a lot of times we need to measure voltage too, monitor the voltage. This is the amp clamp. This is actually the better way to do it. Can you tell where this amp clamp's being connected? This is the starter, right? When you do it at the battery, technically, this is the starter positive, exactly. When you do it at the battery, you know, there's other things those amps are going to, but they're small. But the best way is to do it right at the cable where it goes to the starter. That's measuring only the electricity that's going to the starter. So any amps that go through here are just for the starter, which makes a lot of sense. And then when we go ahead and we're going to disable something. So if you don't disable something, it's going to crank for a second and start, right? We need to disable, like in this case, disconnect the coil so it'll crank and crank and crank and crank. You got to crank it for, a little bit of time. Fuel pump relay, maybe disconnect the injectors, right? Make it so the car will crank but not start, and then you can do this test. Cool. And then this one's measuring amps. This one actually pulled a lot, 300 something amps. That's a lot. Don't do it for more than 10 seconds though. That's really hard for the starter. You're asking a lot of that starter. Cool. So we get the reading, as you can see. And then here's a little guide that I pasted in. We're going to cover this 2 times. So a 4-cylinder engine, 150 to 185 amps. You don't totally have to memorize this, but at least get the gist of it. 150 to 185 amps is the max. Normal, probably less than 100. Right? A 6-cylinder, a little bit more amps. It's more cylinders. There's more compression strokes for it to overcome. So 160 to 200 should be less than 125 if it's really good, but this is the max. A V8, 185 to 250 is the max, but it should probably be more like 150. But if you were to get one and it were 200, like it's okay. It just seems a little high. Now let me, I'm gonna explain this 2 times. Let me just say, if it should be a max of 150 to 185, and you're getting, let's say, 250, is that good or bad?
All right, ain't it? Because there's certain amps come with that higher amperage.
This is a 150 to 185 max for a 4-cylinder. So 250 would be okay for a V8. It might be no good for a 4. So if we have too many amps, generally, that means there's something causing it a lot of resistance. You guys ever used a drill? Use a drill, and when you put a lot of load on it, you hear it strain, and it kills the battery faster, right? You pull more amps when there's a resistance mechanically on the motor. Make sense? High amps means maybe your engine is starting to seize, or there's maybe your bushings are worn in your starter, and it's hard for it to turn. Make sense? Now, if you had, it's saying like 150 to 185 is the max, but it's usually less than 100, but let's say it only pulled like 30 amps and it wouldn't even start. That would be too low, right? Too low amps probably means there's excessive resistance and excessive voltage drop. So if the amps are low, it's probably electrical resistance. And if the amps are high, it's probably mechanical resistance. See how there's a big difference there? So one of my neighbors, I think I probably told you about this car in a couple different ways, but he called me for a no crank, no start on his Tundra. And I told him, like, no crank, no starts are so easy. It's going to be the battery, it's going to be the starter, it's going to be the wiring. It's not going to be a big deal. So I'm just like, yeah, I don't have time for this, but sure, I'll knock it out for you. When's the last time it has started? And he said, oh, it hasn't run in 6 months. What do you think about that? hasn't run in 6 months, that battery's gonna be stone dead. And I go over there and it's pulled right up to his garage door and I can't really get my jumper cables on it very well, but I stretch them out and I jump it and it still doesn't start. And I'm like, well, you know what? I don't really trust my jumper setup. They're stretched to the max. They're barely on there. Like, it probably makes sense just to put a starter in it, but I mean, put a battery in it. I don't think that the battery is gonna fix it though, because you're telling me when the battery was charged, it just clicked, but it's just so hard to diagnose it with a bad battery. So put the battery in, we put the battery in. I no longer had to try to stretch the cables out and jump it. We go to crank it, it goes like this. Click, click. What are your thoughts? Could be the starter. The battery's good. Now if I wanted, I could test the battery and the battery voltage was good. The alternator doesn't come into play yet because it hasn't even started yet. So if the battery is brand new and it's fully charged and it still won't start, I could start doing a lot of different tests. But one test I could do is this amp draw test. And so if I put my amp clamp on there, and this is a V8, so it should be 250, right? 250 max, and this thing was like 350. Why is it pulling so many amps? You think it's maybe a bad cable or something? Remember what I just said. If it's pulling a lot of amps, it's mechanical resistance. It's like something, that engine's hard to turn. So my next step, I went with my breaker bar. I put my socket on the crankshaft and I went to turn the engine. You know what happened? Locked solid. Hard to turn means high amps, right? So the fact I had high amps, I'm like, let me turn the engine. I tried to turn it, couldn't move it. Engine was locked up solid. So I said, well, maybe the alternator locked up, in which case it would be hard to turn the engine. So I took the belt off and it was still hard to turn. Then I said, you know what? I think this engine's locked up. Let's drain the oil. You know what came out? Delicious looking black glitter. And I was like, hey, what happened when you parked this? And he's like, I don't remember. So my point kind of being, you can't really pester the customers too much. They're going to lie to your face because they think if they tell you what you want to hear, it'll be cheaper. And I should have told them, like, dude, you called me like on a Sunday. I didn't really have time for this crap. You should have told me that you had it towed home and it died on the road. And I would have told you, well, your starter doesn't make the car die, but he didn't really tell me the whole story. Luckily, I'm familiar with these tests, and I said, like, whoa, 350 amps, something's mechanically binding. So pretty quickly in his driveway, I'm like, hey, your engine's locked up. What do you want to do? And he's sort of like, I'm not going to fix it. It's a 250,000 mile 2005 Tundra. And I was sort of like, no, I don't blame you. It's going to be, those engines are going to be like $3,000 minimum, maybe 3,500. That's for a used one. And that's not a low miles used one either. So I don't know that if you're not looking to put like $5-6 grand into this truck, I wouldn't fix it. And he said, well, I think it's only worth $5 anyway. Yeah, it's a bad engine. Your diagnosis is for sure. Makes sense? I didn't get super sidetracked, and this helped me stay right on task. Then I told him? Well, he says, what's my bill? And I said, well, it depends. What you going to do with the truck? You know what he said? I'm going to junk it. And I said, how about this? I'll pull the battery out, give it back to you. You can return it because the battery's perfect, and I'll take the truck and no bill. We're good. So that's how I got my Tundra. And I did put an engine in it, but I told you they were expensive. So I put about $3,000 into the truck, but now I could drive it. Make sense? So knowing this stuff could be a big win for you, if you will. Cool. So it gets a lot into the voltage drop testing. So just remember the high current circuit and the low current and the control circuit. The high current, that's talking about the big cable. The control circuit, what do you think that means? That's the one that makes the solenoid, right? Remember how the ignition switch and the park neutral and the clutch switch and the ECM potential, they all control this control circuit. Make sense? So you want to make, as soon as possible, a determination which one it is. So with that Tundra, I cranked it. And you know what it did? Click. So is my solenoid working? At least the solenoid's getting power because I heard it. Now, I don't for sure know that the solenoid's definitely good, but if the solenoid's clicking out there, I know that the voltage is making it all the way to this little S terminal. I'm not real worried about the neutral safety and park and none of that type of stuff. I'm like, that starter's getting the power it needs. I could voltage drop test the high current side though. What if that battery cable was bad? That would make it click. But if the battery cable had a lot of resistance, what would be the amps? High resistance means Low amps, exactly. So I did the quick amp check and the amps were high and I'm like, I'm not really worried about resistance because the amps are high. I'm worried about like mechanical resistance. Kind of makes sense? So that amp clamp tells you a whole lot. Cool, so the high current, battery, cable, starter solenoid, the solenoid contacts inside and the heavy ground cables. The control circuit, the little switches, the PCM, the small wire, small current. Part of the relay, you know the relay parts. Cool, so there's your high current. And then we could voltage drop the high current side like we kind of talked about. The high current side's more susceptible to voltage drop because it has a lot of current. Makes sense? It's just, we have a lot of demands on that side. Not so much on the control side. Cool, but to really test it, you have to be cranking it. That's when we need, hey Tony, can you hold it to crank and then let me measure the voltage drops? Cool. Here's how you do it. Look at this positive cable. We're going to connect the meter, put the black lead to the positive battery post and the red lead to the starter right here where the actual motor turns. Not the big terminal, but the actual starter motor terminal right here. Okay, and then we're going to put on voltage drop. Put the meter on voltage and crank it. How many volts did this one drop? Can you tell? Do you know why it's a negative, by the way? I probably would have put the red lead on the battery and the black lead on the starter, but whatever. It's a negative 0.158. So that's like what? Not even 0.2 volts. That's 1.5 volts, basically 1.6 volts. That's great. Battery cable's good. Battery terminals are good. All the high current side of the positive is good in one test. Cool. Now you guys can kind of see what happened there, right? Just that. That's it. Boom. Okay, and then we could check the ground side as well. So for the ground side, you need to put your black lead. I think we should check the ground side. If it was your ground side, you need to put your black lead on the case of the starter, and then put your red lead on the battery terminal negative, or probably what I would do is the black lead on the battery right there and the red lead right there, and then crank it, and you should have a minimal voltage drop too, like maybe the 0.2 like we had said. Right, so if you were to look at it like this, if we were testing the big positive in and the actual motor, so on this, we would actually voltage drop this terminal and this terminal. What are we actually checking right there? Do you guys know? What connects these two and we do voltage drop? What component connects this to this? Not the disc inside, which is part of what? The solenoid, yeah, exactly. This solenoid can have a bad contact inside, so we need to also check these two. So if you were to have too much voltage drop, you need to know, is it the solenoid? Is it the cable? Is it the battery terminal, right? This one checks the solenoid itself. Cool, that's a good one. The voltage drop will tell you a lot. Okay, this one I liked. What do you guys think about this wiring diagram? Is this simple or complex? This is a wiring diagram that would be like on the ASE, so you know. You could break this down and be like, what if I were to say we had, first off, let me just trace it so you're familiar. See the positive, right? Positive goes here, goes to the starter solenoid. This disc right here, as we called it, that was good. That connects B to M, right, when we activate the solenoid, and then M gets the power here. And then this case is grounded. But on the control side, it's got to go up. It comes over onto Z. This is the park neutral switch right here. It goes down to the relay. So if we get 12 volts on the relay, this relay right here should get ground, right? If it gets 12 volts here and ground here, that should swing this over. Then if you look, that comes from B plus, positive, goes through here, which if it's connected, B plus is going to go over here and actually activate that solenoid. Now, I'm going to do this in two ways. One, if I were to say our reading on Z is, let's just make Z a 12 volts on Z, but at C11, see this right here? Let's make that one a 0 volts with our meter. What do you think could be going on?
Something's wrong with the park reverse neutral. There's something.
Yeah, you could call that the Prindle switch or the neutral safety switch or the park Prindle. Look at it. Prindle, not Pringle. Prindle, like that. Okay, so yes, I agree, right? So just so you can reference this, everything we've been kind of grinding in here in the classroom for a lot of weeks. If you understood that, that's a potential answer to an ASE question right there.
So what would be? It wouldn't be connecting, right?
Well, it shouldn't go from 12 volts to 0 volts across the switch, right?
So it means it's open.
Yeah, or like excessive voltage drop inside the switch, just like what we tested on the board. Yeah, you got it. Now let's just say we had, I'm gonna look at this really quick. Let's just say we had 12 volts on W right here, and we had 0 volts on Y. What do you think that would indicate?
The relay?
I would say so, right? Because if you look, 12 volts should come through here, should go to here, should go up through the relay. But the problem is the relay latched or not? Is the relay active? Then we don't really know, right? So we might have to do a little bit more looking into it. So if we were to really trace it, and it were to go here, and then if we're in park, it should go through here, right? And then it should go to the relay. And then if you look on the out of the relay, you see this? This is grounded, right? So this should go to here. So shouldn't this be magnetized? And if it
something with the switch, it might be
corrosion on the contacts right there. Maybe something's wrong here. Maybe this little switch right here is broke off inside the relay. Absolutely. So if we have 12 volts here and 0 volts here, the relay's got a problem.
Definitely in that relay.
Exactly. So if we fix it, now it goes up through, then we'd no longer, let's just say I had 12 volts at 87, but 0 volts at C26. What do you?
Between
The wire.
the wire.
Yeah, exactly. Bingo. See, so like, just to tie this into what you're saying, this is replicated directly from the ASE, okay? So they could ask you 10 different questions on this, and they'd be like, you have 0 volts here, you have 12 volts here, you know, you gotta understand it's the wire, or it's the switch, or it's maybe this switch up here is not activating the solenoid, okay? So you guys have learned a lot, you just, you know, might need a little confidence boost if this is what you're gonna try to do. So I liked this diagram because this is the whole starter diagram. Now, if we were to trace overall, so you understand it, B plus, right, should go up, over, down, should go through this because it's in park and it's good and it's adjusted, go to the relay. The relay gets ground through 85 to sheet metal. That activates this. It pulls this over. Now that's all we know. Then let's come from B plus again. B plus goes over here to the starter. It's there all the time. But B plus also goes down, over. Okay, now as soon as it latches, it should go through. It should go over. It should go up, over, and hit the solenoid. Now if the solenoid, if you look at it, it's grounded to the case right here. So now if our solenoid gets 12 volts on the S terminal, what's it going to do to this coil? And it's actually going to pull upward exactly, which is going to connect the big B plus to right here. And you know what this thing does? Just like that. That's your whole diagram right there. And then of course we got ground to the case. And then we got ground on the battery going to the chassis and the block, which is how these ones are going to connect, right? So they would, and they would, that's your whole diagram. If you understand that diagram, then somehow somebody has either done their work or maybe I've done my job somewhat. You'd be surprised, a lot of people don't understand that diagram though, just letting you know. I have no idea because they're not really putting in the work to understand it. Cool?
You forgot the.
Ah, this solenoid's stuck on. Fun times? Very fun times. Okay, here you go. Here's that similar thing except drawn in prettier color, right? Positive through the fusible link to the switch. If you turn on the switch, that'll activate the relay. If you activate the relay, that should latch this switch, which would send 12 volts down here to the solenoid. If you get 12 volts at the solenoid, this big B plus goes through that little disc we talked about, and that runs 12 volts right to the motor. Yeah, and then so the solenoid does two things. Remember, punches this out so it engages a flywheel, but also connects this terminal with this terminal and gives the motor the power to spin, right? We have 12 volts on here all the time. The question is the solenoid going to actually close this and connect the two and also kick it out, right? So that's why we need this small wire. Cool, kind of makes sense? Some of it's a little bit redundant, but making sure you really understand it. And this one is just kind of showing you can do a couple different tests. You could do voltage drop on this. I mean, you could test the circuit kind of in the ways that you want to test the circuit. Voltage drop is a good one, available voltage is a good one, etc. Here's another diagram. Do you notice this diagram looks different, but it's actually kind of the same? Here's your battery. Red goes to the starter and it stays there, but red also goes through a fuse, through the ignition switch. It goes either to a Prindle for an automatic or through a clutch switch for a manual, which is then going to control the hold-in coil and ultimately the relay. I think they might have eliminated the relay here, but it's the same type of thing. This control circuit has to light up that S terminal, the small wire. And if the small wire gets 12 volts, then it pulls in, connects the big B plus to the big starter motor B, kicks it out and spins it. Just like that. Kind of repetitive. Again and again. Now to do the relay though, we did talk about this. Right here, we're testing the relay coil. So you see that 83.7 ohms? That's the winding. On the diagram, what that looks like is this. We're testing this from here to here. If this relay coil is like totally blown out, what do you think the reading would be?
0.
0 would be shorted. OL, yeah, OL. So a lot of ohms. If it's like a bulb, if it's got a blown filament, it'd be a full OL. But right here in this test, we got some number, 83.7 ohms. Fine, okay. Is there a spec? Maybe yes, maybe no. You could probably compare it to a known good.
So that 83.7 means it's good?
It means there's continuity on that coil. So if you look at this coil, if this coil was open, you'd get OL. At least if we measure the resistance of the coil, we know there's continuity there. It doesn't totally ensure that it's pulling the switch side of the relay over, but it's a good indication.
So that's your starting relay, right?
I would go ahead and I'd check the coil resistance. It's easy. Then once you want to check more, it gets tricky. Okay, so I like this picture because what we did is we put what's called a relay test block in. We pull the relay out. We put this test block in, we put the relay back in, and it exposes these little test points, which are just a bit hard for you to see right here. So I'll make them so you can see. Right here, you see these little terminals. Now we're able to test those relay points with the relay plugged in. Now, if we go to crank it, we're going to give positive and negative that coil, and that should close the switch, right? Now, how would you know how much the switch is dropping without being able to close it, right? So the way that we did it, with the relay off the car is we used a little jumper and we jumped the relay closed. And you could do that. But in this case, we're able to reinsert the relay, hold the key to the start position. That should magnetize the coil and close the switch. And then right here, we can voltage drop the switch. We can even test to see if the relay is getting its power. So if I were to back out right here, that relay tester just basically sets the relay back in and it gives us access to here, 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 and here. In the start position, shouldn't we have 12 volts here? The relay tester gives us that ability to probe that. Shouldn't we have ground right here? Cool, if we have 12 volts and ground right here, that tells us this control side's good. Then we can see, do we have 12 volts here? If yes, good. But if here we don't, then we're like, what's up with that relay? That relay switch is no good. It's the same test we talked about. But you can do it right there in the fuse box because it's got this nice adapter right here. It's a cool adapter. Cool. And then we can see what's available, what's voltage dropping, etc. And let's just say it's making it through the relay okay. Then we can come down here and see what's available on the battery terminal, or probably better yet, we could actually see what's available on the small terminal, which is really hard to see right there. So I'm going to go ahead and do this again. Right, but we got this lead I would put on the small terminal. The small terminal is the control terminal. That's the solenoid one. Cool, so that would get your diagnosis right there, pretty much. And if it's got 12 volts there and it doesn't work, the starter's no good. If it doesn't have 12 volts, you got to back up and check other stuff. Okay, that's really the summary. And then if you wanted to be if you wanted to double check yourself because you weren't confident, you could take a jumper wire and jump it to the B+, and then jump it down here to the small terminal. We're trying to show the small terminal there, and that should actually activate the solenoid. So you're just basically jumping 12 volts to the solenoid. So like on a diagram, the way I would show that is right here. We agree we should get 12 volts there in the crank position, but let's just say we don't. Couldn't I take a B positive and just jump it over? If I were to jump B positive to this yellow wire, what should happen? Chunk, chunk, chunk. You know, like chunk, 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 chunk. And then if it's going chunk, chunk, and you see it move, you know the solenoid's good. Then you're like, oh yeah, for sure it's because I don't have power here. See what? So there's a couple different. You shouldn't really need to do that, but if you just want to double check that the solenoid's good, you can. You can jumper it like that. Just make sure you're seeing there. It's hard to see in this picture, but this is the S terminal. This is not the big battery. This is not the big motor terminal. If you tried to use that little tiny wire to jump this big battery terminal to this motor terminal, that wire ain't big enough. That wire is now the fuse, and it's melted. And so is your hand. Cool. Now, if we want to R&R a starter, remove and replace, of course, disconnect the negative battery terminal. Access the starter, you got to pull that small terminal, pull the big terminal. There's just a couple terminals. It's not a real big deal. One of the tips and tricks I can give you on that is these are kind of hard to get to. So sometimes what I'll do is I'll unbolt the starter. I'll disconnect the battery. If you don't disconnect the battery, you're asking for trouble because this is a big positive cable that's unfused. And if your wrench goes from big positive to anywhere on chassis ground, you're welding. And welding could be fun, but that's not what the customer came in for. So disconnect the battery. I like to disconnect the starter and get it so I can move it like this. And then I'll be like, aha, and then I can get these a little easier. Make sense? Rather than fight them. But you just got to keep track of where they are. When you put them back on, if they were like this and you put them back on like that, you might not realize it because it's not in place, and you could have some such touching that's not supposed to be touching or whatever. So the R&R on the starter is not a real hard job typically. But some are more difficult than others. You see this starter right here? Yeah, 2UZ Toyota V8. You got to pull the injectors, fuel rails, manifold, throttle body. They also do this on North Stars. Quite a few manufacturers decided we'll put the starter all up under that business because that's what it is. Yeah, 4.7. Yeah, the 2UZ. This one was that Tundra that I bought. So remember how I told you I was diagnosing the guy's starter in the driveway? I was kind of like, no, I was able to do the amp clamp test. So see, the diagnosis saved me from having to actually get at the starter to do a parts cannon job or whatever. So like, yeah, I agree. Most starters are easy, but not so much on this one. You know, so it ended up being not a starter problem at all. And now this is one that I want to make sure everybody gets. The difference between an electrical problem and a mechanical problem. Okay, so an electrical problem. Loose connection, dirty connection, corroded terminals, a discharged battery, faulty motor, faulty starter motor, faulty control unit. That's all electrical problems. Or it could be mechanical problems. Seized pistons, bearings, hydrostatic lock. You know what that means? You sucked up water and it's hydrolocked. It won't start. Don't ask me how I know. Trust me, I know. A couple times. Incorrect ignition or valve timing if it's really bad. A seized alternator or another belt-driven accessory. So like, let's say that your alternator seizes and the belt's on, or your water pump seizes and the belt's on. It won't let the engine turn. This is all mechanical stuff. Make sense? The Tundra was this. I was really sure it was going to be this because it sat for 6 months. But when I did my amp clamp test, it told me, oh, my problem's not up here, it's down here. The name of the game is eliminating as many possibilities as quick as possible. Make sense? So I could say, oh, to diagnose your starter, I need to test for loose connections, dirty connections, corroded terminals, discharged battery, faulty starter motor, faulty control unit. I need to also test seized pistons, bearings, hydrostatic lock. If you go to test all these things, you're going to be there all day. And that's going to be kind of hard for you to justify. So what I'm going to come in and do is I'm going to try to eliminate this or eliminate this like in one test. Does that sound fair? Make sense? So if I want to do one test, I'm going to go ahead and do that amp clamp test right here. And if you'll remember, if we have the spec and it's pulling low amps, that's electrical resistance, excessive. But if it's pulling high amps, that means there's a mechanical something that's causing the high amps. Make sense? So down and dirty real quick, how many amps that starter's drawing will tell you if it's mechanical or electrical within just moments.
So like the big tester thing, would that tell you if our starter was going bad or not?
The big tester thing that we have will tell you the amount of amps, and it'll say pass or fail, but it doesn't exactly come up on screen and say, hey, your amps are low, check for electrical faults, or your amps are high, check for mechanical faults. You have to know that. And actually, a lot of technicians don't even really know that. All right, so when we talk about how it sounds though, like if you jump in the car and you do a slow crank, and it's like, it could be the engine locked up, huh? But it could also be a corroded battery terminal. Let's say the engine's almost locked up. The engine's starting to seize. It could go, it'll sound the same as if we had a bad battery connection. It'll sound, but if you did the amp clamp, if it's a bad electrical connection, it's going to be low amps, and if it's a seizing engine, it's going to be high amps, right? That's kind of what that's saying. So high amp draw. Oh, and it could also be the starter too. So if this starter has these bushings and these bearings and things, if this starter bearings and bushings are starting to fail, this will cause the amp draw to be high. So it's not just an engine, but it'd be more like mechanical. Makes sense? At that point, you'd actually really need to turn your engine and see how it feels when you turn it. If your engine feels kind of normal, but it cranks slow and it has high amp draw, that starter's probably starting to seize up in its own bushings and bearings. Okay, make sense? And so, yeah, just understand slow crank and no crank can be caused by both mechanical and electrical. And this is your cheat sheet right there, just for you. Okay, now other things that we don't go real crazy into detail, but you have to know. If you go to start the car and it's a no crank, no start, it could be the fuse, the battery, the whatever, the this thing, that, the cable, the connections, the solenoid, the starter. It could also be security system. So if you jump in, you go to crank it, and you get a light that looks like this, or this, and it's a no crank, it's just nothing, there's a good chance, remember the PCM, the ECM or the computer controls the starter now. So if you have an incorrect key, an unprogrammed key, a failure in the security system or whatever, it can cause a no crank, no start. So if you roll down to O'Reilly's, you get a starter, you put it in, and then you still have this light on, it's sort of like, hey, you just wasted all that money and time. Make sense? So watch for these lights. If it does have these lights, does anybody know what the next step would be?
Call service.
For you guys, scan tool. Get the scan tool out, see what codes are set. If this light's on, it's going to set a DTC. Incorrect immobilizer message. Incorrect key, unprogrammed key, something like that.
Can that also cause a engine light?
It generally wouldn't cause check engine, it would cause one of these specifically. So if there's a fault in the security system, these are some of the warning lights you may see. And it may, because remember it's computer controlled, it may prevent the starter from functioning, okay? And in other ones, it'll actually allow the starter to work, but it'll prevent fuel. So it might go sha-na-na-na-na-na-na-na-na-na, but not start. On other times, it'll let it start, and then it'll kill the fuel in like 3 seconds. It'll be like, and if one of these is on, that's all security system, it's basically preventing the car from being stolen. We don't want the car to be stolen. We're tired of the thieves stealing the cars. They're getting away with it. But yeah, they got some tricky ways to do it now. So if you're just overlook, part of the system, we got a key, and it does have it. We'll call it a chip. There's a transponder. There's a mechanism in here. when we go ahead and we insert the key, we're going to put it into the lock cylinder. And when we turn it, this is going to verify that the chip passes by. So like the chip is actually going to pass by a sensor. So it's going to check for timing. The second that the chip passes by the sensor, that ignition switch should close. And that's so that like you don't have the customer or the thief drill out the ignition switch and just hold the key up there and turn the ignition switch with a screwdriver, right? So there's various levels of how sophisticated this can be. So if this chip is no good, or if you got a new key cut and this chip has not been, you don't learn the chip doesn't change. But if the car isn't programmed to recognize the chip, it still won't start, right? So in here, we got that coil, and that's gonna detect the chip, make sure it's the right chip, make sure it turned at the right time. Then when it sees that, it's gonna give a signal and say, yeah, that's legit. It's gonna send that signal to the ECU, and the ECU is gonna say, oh, I've got like my immobilizer permission passed, or I got my pass key or my pass lock approved. If you don't, it probably either won't enable the starter or it won't enable the fuel, and it will start, but it'll stall. Kind of makes sense? So it could be a security thing. So just be aware of it. If you really want to get into security, every vehicle is a little different. You got to really understand that one. Check for codes. If it gives you security related codes, you're going to have to pursue those codes. And with that, you guys made it. Go ahead and pause me. All right, I had that wrong. So if I hold this right here, you see that little P? We want the P to be on, that's the peak. This one's a little different than I'm used to. Okay, we go again. Oh, and also, see that number right there? We really need to zero it out. 0. Come on, sweetie. This one hasn't been real impressive. Let's just turn it off. Turn it back on. DC amps. 0. Okay, there we go. So now it's delta. That's true 0. Now we're going to put it on peak. See that P? There we go. Okay. Now the arrow should go towards away from the battery, towards the starter, the way the electricity flows. Louise, go ahead. Okay, good. 45 amps. 45 amps is way low. So what do you think that means? Engine seized or a resistance in the system? Electrical resistance or mechanical? Electrical resistance, I agree. Yeah, because it's low, right? It's low. There you go.
So we are 150 max.
And you heard that click, right? But it doesn't actually start. So if we were to lift it up and we were to hook this up, how much voltage was available on the small terminal?
11.9.
Okay. Yeah. Crank it for one more second. Oh yeah, the magic smoke. But you can hear the solenoid click, so you know it's getting voltage on the small wire.
What does it mean when it's smoking? Is it
The magic smoke is out. All right, let me walk you through this lesson. So this HHR was in for a no crank, no start. I caught a bit of that on video. Basically, you'd go to crank it, and it would just click. Okay, so the next step, you'd make sure this is your big positive. We got 12 volts there, pretty much standard. Then we want to see if it gets 12 volts down to this terminal. And in this vehicle, it did. And the other giveaway you can see in the video is it clicks. Like, you'll see the video, it clicks and then it smokes. Once the solenoid clicks, you don't really have a whole lot else to check. It already means that it's getting 12 volts here and it's got 12 volts here. But it wouldn't move. So that led us to understand when this small wire gets 12 volts, this big one will be basically connected to this, which goes right to the motor, right? So when it's trying to turn the motor and it won't move, but the solenoid's working, we got a problem in the motor. And that was the case on this one. And we did try to give it a little bit of a tap, but with the permanent magnet motor, you know, it's kind of sensitive. It didn't really work, but our diagnosis was over, so we went ahead and we put the starter in there. Now I'll go and I'll show you how well it starts. And it wasn't a hard job. Students did it in about an hour, so no big deal. Although, I guess the key fob doesn't work. So here we go. And then that old starter's a core. Actually, I've already got the core in the box. Boom. Okay, so there's the evidence of understanding the system. Makes the diagnosis really easy. And this car is repaired, good to go. Now, what if it didn't click and it didn't have voltage on that small wire? Well, that's when we'd need to get that wiring diagram out and backtrack to where the voltage is lost, right? So if it starts at the battery, goes through the ignition switch to the park neutral or whatever, or if the ECM is not giving the ground, you know, we'd get a little more in depth. But for something as simple as this, good to go.